momentum, for the first subtopic, momentum. First star mark for the first subtopic, momentum. Momentum. So, what is momentum first? Before the conservation, you have to know what is momentum. So, what is momentum? Okay. Now, මේ මොකද මේ වෙන වෙන කතා කර ඉන්නේ මොකද කේස් එක? හරි නේද? වැඩ කරගෙන යන්න. දැන් බලන්න ඉතින්. 4:30 වෙලාව. Okay. Now, when we come to momentum, momentum is the physical quantity derived by mass multiplied by the velocity. Momentum is the physical quantity that we get by multiplying mass by the velocity of the object. Okay. So, here as an equation, momentum is given by P, mass is M, velocity is mv. So simply we say P equals mv. Momentum is the mass into velocity, but this is the case. We have to understand the physical meaning of the momentum. But before that, let's write the equation. Then we'll come to understand the physical meaning, what momentum really is. But as an equation, this is the one. Momentum is equal to mass into velocity, P equals mv. Okay, first finish it. Then we will come to the physical meaning of the momentum. First, momentum is equal to mass into velocity, that's clear. And can you give me the SI units of momentum also? Can you give me the SI units of momentum? As momentum is equal to mass into velocity, here mass is measured by kilograms and velocity by meters per second. So momentum will have the SI unit kg meter per second. Kg meters per second. Write down that also. Kg meters per second. Okay. Momentum will have the SI unit kg meters per second. Okay. Now, what is the physical meaning of the momentum? Have you ever heard about the physical meaning of the momentum? Yeah, easily we can say momentum is equal to mass into velocity. But what is the physical meaning of the momentum? Now, what is the physical meaning of a force? Either a pull or a push. If it is a pull or a push, we say it's a force. What is the physical meaning of displacement? The shortest distance between 2 points. Shortest distance between 2 points. It's a displacement. So what is the physical meaning of momentum? Okay. To explain you the physical meaning of the momentum, I will take this example. To explain the physical meaning of momentum, I will take this example. Okay. Now here, there's a bullet. Here, there's a bullet. And this bullet is 100 grams in mass. There's a bullet which is having 100 grams as its mass. And as it's a bullet, it has a higher velocity, 1000 meters per second. 1000 meters per second. Okay. And this bullet is moving towards a pole. This bullet is moving towards a pole. There's a wall. There's a wall. And this bullet is moving towards a wall. The weight is 100 grams. Velocity is 100 meters per second. And here, okay. Now, there's another one. Here you have a large stone here. Here you have a very large stone. Let's say it's 1000 kilograms. Let's say it's 1000 kilograms. But its velocity is 0.1 meters per second. Now, you are throwing a very large stone towards the wall. Here, it's a 1000 kg stone. Okay. Now, as it is very large, you can't provide the larger velocity for stone like bullet. So, the velocity is 0.1 meters per second. Okay. Both of them are thrown towards the wall. let's see what happens. And from this, we'll try to understand physically what momentum is. Okay, write example. Write example. Example, I'm going to give you the sum. A bullet, 100 grams in mass. What I'm trying to do is to explain you the physical meaning of momentum. A bullet, 100 grams of mass. A bullet, 100 grams of mass is fired towards a wall. Is fired towards a wall. Is fired towards a wall. Is fired towards a wall with a 100 meters per second velocity. With a 100 meters per second velocity. With a 100 meters per second velocity. And again, a large stone, and again, large stone with a 1000 kg mass, with a 1000 kg mass is thrown towards the same wall, is thrown towards the same wall, is thrown towards the same wall with a velocity of 0.1 meters per second, with a velocity of 0.1 meters per second. Okay. Now, before explaining the physical meaning of momentum, draw this diagram, and I need you to calculate the momentum of the bullet. From the equation P equals mv, draw the diagram first, then in the bottom, calculate the momentum of the bullet and the momentum of the stone. I will show you something. Draw the diagram and calculate the momentum of these two objects separately, which are thrown towards the wall. There's a bullet moving towards a wall, 100-gram one. As it's a bullet, it has a higher velocity, 1000 meters per second. And there's another stone thrown towards the same wall. It's a large one, 1000 kilograms. And as it's a stone, we can't throw it with the same speed of a bullet. It's very heavy. So we have thrown it with a velocity of 0.1 meter per second. It's possible. Now we are going to see the momentum values of these two objects to come to a conclusion what the physical meaning of momentum. Okay. Here, the momentum of the bullet. Here, the momentum of the bullet, 100 P equals mv, mass is equal to 0.1 kilograms, and the velocity is 1000. So, you will get a 100 kg meter per second value for the momentum of the bullet. Okay. Now, I'm going to calculate the momentum of the stone. It's equal to mv again. It's equal to mv. Mass of the stone is 1000. Velocity of the stone is 0.1. So again, you will get 100 kg meter per second. 100 kilograms meters per kg m s minus 1. Now sometimes, okay, finish it. I'll explain the lesson again. Puta, then up the balagan. Okay, pute podam mulate. Okay, today we are in the lesson linear momentum conservation. Okay, the first thing, what is momentum? The physical quantity momentum stands for the mass into the velocity of the object that we are calculating the momentum. Momentum is equal to mass into velocity. So in a format of an equation, momentum P is equal to mass into velocity, mv. P equals mv. Okay. If it is P equals mv, the equation, mass is measured by kilograms, velocity meters per second. So the momentum will have the SI unit kg meter per second. Okay. Now, as an equation, we know momentum is equal to mv. But as a physical quantity, what this momentum really stands for? That's the big thing. Okay. Now I have given you an example to show you what really momentum is. Here in this example, there's a 100-gram bullet fired towards a wall with a 1,000 meter per second velocity. And again, there's a heavy stone thrown towards the same wall. As it is heavy, you can't provide the velocity like a bullet. So it's a smaller one, 0.1 meters per second. Now both of these stone and the bullet are moving towards the ball. For that, to show you something, I have calculated the momentum of these two objects separately. As this bullet is having a mass of 100.1 grams, 0.1 kilograms into the velocity 1,000, 100 kg meters per second. And again, as this stone having a mass of 1,000 and a velocity of 0.1, okay, what is the momentum? 100 kilograms per kg meter per second. Okay. Now, by looking at these two examples, can you say something about momentum? Now you know if this bullet hits the wall, there will be a certain damage. If this bullet hits the wall, there will be a certain damage. Why? Even though its mass is less, it has a higher velocity. Due to its higher velocity, the wall will be damaged. Now here, the bullet doesn't have a mass, a large mass. It's a small mass. But if it hits the wall, there will be a certain damage to the wall. Why? As the velocity of the bullet is high. So the damage is high. Damage is high. Again, now you are throwing the stone towards the wall. You are throwing the stone towards the wall. When you are throwing the stone towards the wall, what happens here? Again, there will be a damage to the wall. There will be a very large damage to the wall. There, how this damage happened? Even the velocity is less as the mass is high. Again, the wall was damaged. Again, the wall was damaged. So, in both cases, what you can see, momentum values are equal. Momentum values are equal. Momentum එක කියලා කියන්නේ මොකක්ද දන්නවද? Momentum එක කියලා කියන්නේ මොනවා හරි දෙයක් ගිහිල්ලා තව කෙනෙක්ගේ වැදුනහම වෙන ඩැමේජ් එක වගේ අදහසක්. Momentum එකේ physical meaning එක මොනවා හරි දෙයක් ගිහිල්ලා කොහේ හරි තැනක වැදුනහම ඒකෙන් එන ඩැමේජ් එක වගේ අදහසක්. මේ බලන්නකෝ. මෙයාගේ weight එක අඩුයි. හැබැයි velocity එක වැඩි, damage එක වැඩි. ඔයා දන්නවා bullet එකක් wall එකක වැදුනොත් damage එක ගොඩක් වැඩි කියලා. ඊළඟට මෙයාගේ weight එක වැඩි. හැබැයි velocity එක අඩුයි. හැබැයි ඔයා දන්නවා ලොකු stone එකක් bullet එකක වැදුනත් මේ බිත්තියක වැදුනත් ලොකු damage එකක් වෙනවා කියලා. ඒ කියන්නේ velocity අඩුවෙන් තිබිලත් damage එකක් වෙන්න පුළුවන්. velocity අඩුවෙන් තිබිලත් damage එකක් වෙන්න පුළුවන්. ඇයි? mass එක වැඩි හින්දා. mass එක අඩුවෙන් තිබිලත් damage එකක් වෙන්න පුළුවන් බිත්තියක වැදුනොත්. ඇයි? velocity වැඩි හින්දා. එහෙනම් ඇත්ත කතාව අර බිත්තිය වැදුනහම damage එක වැඩි වෙන්නේ mass into velocity එක. mass හරි velocity එක හරි දෙකෙන් ඕන එකද. හරි? ඇයි? momentum එකෙන් තමයි මේ damage එක cause කරන්නේ. තේරුණා නේද? කවුරු හරි අහුවොත් එහෙම මොමෙන්ටම් එකේ ෆිසිකල් මීනින් එක මොකක්ද කියලා. ඔයාගේ වයසේ ඕනෙම ළමයෙක්ගෙන් අහුවොත් මොමෙන්ටම් එක කියන්නේ මොකක්ද කියලා mass into velocity කියලා කියයි. හැබැයි මොමෙන්ටම් එකේ ෆිසිකල් මීනින් එක මොකක්ද කියලා අහුවොත් උඩබිම බල බල ඉන්න එකක් තමයි බොහෝ වෙලාවට දැකලා තියෙන්නේ. මොමෙන්ටම් එකේ ෆිසිකල් මීනින් එක කියන්නේ මෙන්න මේකයි. ඒ ඔබ්ජෙක්ට් එක ගිහිල්ලා කොහේ හරි තැනකට කොලයිඩ් වෙච්චහම වැදුනහම එයාගෙන් ඇති වෙන ඩැමේජ් එකේ amount එක පිළිබඳව මෙෂර්මන්ට් එකක්. මේ සමහර වෙලාවට smaller masses but as the velocity is high the damage is high. සමහර වෙලාවට larger masses but velocity is low but again the damage is high due to the mass. So the damage is caused by the mass as well as the velocity. So mass into velocity is the cause of the damage. That's what the meaning is. Okay. You can write a small star mark after this. You can write a small star mark after this. Even the bullet has a lower mass. 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 Still the damage is high. Even the bullet has a lower mass. Still the damage is high when it collides with the wall. When it collides with the wall. When it collides with the wall. As the velocity is a higher value. 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 Again, when the stone collides with the wall, and again, when the stone collides with the wall, and again, when the stone collides with the wall, and again, when the stone collides with the wall, the damage is high. The damage is high. The damage is high. As it has a larger mass. As it has a larger mass. Even though the velocity is small. Even though the velocity is small. Even though the velocity is small. So it seems, even though the velocity is small, so it seems that the damage is done by, so it seems that the damage is done by mass or the velocity. That the damage is done by the mass or the velocity. That the damage is done by the mass or the velocity. Actually, the momentum means, the damage caused to a certain surface. Actually, the momentum means the damage caused to a certain surface when the object with the certain momentum, when the object with the certain momentum, collide with it, when the object with the certain momentum collide with it, when the object with the certain momentum collide with it. Momentum is the multiplication of mass and velocity. Momentum is the multiplication of mass and velocity. And in these both cases, it was a higher value. In these both cases, it was a higher value. And the damage was also high. And the damage was also high. And the damage was also high. Okay. Hard. දැන් මම ආය පාරක් පරක්කු වෙච්ච දරුවන්ට මුලින් ඉඳලා විස්තරය කියනවා. බලා ගන්න. පරක්කු වෙච්ච දරුවන්ට ආය මුලින් ඉඳලා විස්තරය කියන පුතේ කැමරාව ගමු මේ පැත්තට. හරි. අද මුලින් ඉඳලා වටයක් අහගන්න. අපේ පාඩම ලියා ගන්න වෙලාව දෙන්න. ඉස්සෙල්ලා අහගෙන ඉන්න පුතේ. හරි. ඊළඟට වැදගත්ම කාරණේ. දැන් ඔය ටික ඉතින් පරක්කු වෙලා එන ඒවා හදා ගන්න වෙනවා. දැන් දවස් කීපයක් ඒක කියලා තියෙනවානේ. එයි දන්නවද කාරණේ? හරි. මේ පාඩමක මුල මිස් වෙන එක මාර පාඩුයිනේ. මම මුලදී චුට්ට වෙලාවක් බලන් හිටියා. බලන් ඉඳලා ඉවරලා ටික කියා දෙන්න ගත්තා. මම දැන් මේ ආය පාරවල් කියනවා. පුළුවන් තරම් මම ඒක මේ අඩු කරලා දෙන්න බලනවා. නමුත් ඒක අර තමන් ඇවිල්ලා වේගෙන් ඉඳගෙන එහෙම වෙච්චාම පාඩමේ මුල හරියට ෆීල් වෙන්නේ නැහැනේ. ඒක හොඳ ළමයා වගේ හදා ගන්න. හරි දැන් ආයෙ බලා ගන්නකො ලොකු කතාවලට යන්න නැතුව මේ වැඩේට බහිමු. හරි බලා ගන්න ආයෙ මුලින් ඉඳලා තරක් වෙච්ච දරුවෝ. හරි මෙන්න හරි අපේ පාඩම linear momentum conservation. එතකොට සිලබස් එකේ මේ පාඩම තියෙන්නේ මොමෙන්ටම් කියලා විතරයි. මොමෙන්ටම් කියලා විතරයි. ඉතින් මොමෙන්ටම් විතරක් ඉගෙනගෙන බෑ. ඒකේ කන්සර්වේෂන් එකක් තියෙනවා. ඒක ඉගෙන ගන්නට ඕනේ. හරි. දැන් එතෙන්ට එමු. ඊට පළවෙනි එක මොමෙන්ටම් එක කියන්නේ මොකක්ද? මොමෙන්ටම් එක කියන භෞතික රාශිය මොකද? The physical quantity momentum, what it means. Momentum is the mass into velocity multiplication. If the mass of the object is multiplied by the velocity of that object, you will get the momentum. So momentum is symbolized by P equals mv. What are its SI units? Mass is measured by kilograms, velocity is by meters per second, so kg meter per second. So that's the one. Momentum is into mass into velocity. The next important thing, what is the physical meaning of the momentum? දැන් මෙන්න මේක හිටපු අයයි අලුතෙන් දැන් පරක් වෙලා ආපු අයයි ඔක්කොම ලහගත්තා නම් හරි මේක හොඳ එකක්. හරි? භෞතික physical meaning එක මොකක්ද momentum එක කියන එකේ. මේක explain කරන්න මම example දෙකක් ගත්තා. මම ගත්තා mass එක පැත්තෙන් ගොඩක් අඩුවට තියෙන. mass එක අඩුවට තියෙන velocity එක වැඩි bullet එකක්. මෙයාව මම බිත්තියකට fire කරා. මම දන්නවා bullet එකේ mass එක අඩු වුණත් velocity එක high හින්දා ලොකු damage එකක් වෙනවා කියලා. damage is high mark කරා එතන. ඊට පස්සේ මෙතන මම ගත්තා 1000 kilogram stone එකක්. ඉතින් ලොකු stone එකක් හින්දා මට bullet එකක් වගේ වේගෙන් විදින්න බෑනේ. පොඩි velocity එකකින් තමයි යවන්න පුළුවන්. 0.1. හැබැයි මම දන්නවා ලොකු stone එකක් ගිහිල්ලා බිත්තියක වැදුනත් බිත්තියට ලොකු damage එකක් වෙනවා කියලා. එහෙනම් මෙතන බිත්තියට damage එක කළේ mass එක නෙමෙයි. 100 grams වලින් මොන damage ද? යකඩ මේ ගඩොල් බිත්තියකට velocity එක තමයි damage එක කළේ. එහෙනම් මෙතනත් velocity එකද damage එක කළේ. මම දන්නවා bullet එකකින් වෙඩි තිබ්බත් බිත්තියට damage වෙනවා. ලොකු stone එකකින් ගැහුවත් බිත්තියට damage වෙනවා කියලා. හැබැයි ඉතින් මෙතන බිත්තියට damage එක කළේ bullet එකේදී velocity එකනේ. එහෙනම් බිත්තියට මෙතන damage එක කරන්නත් ඕනේ velocity එක කියලා හිතුවොත් මම වැරදි. ඇයි velocity එක 0.1 velocity එක හරි පොඩි. එහෙනම් මේ ලොකු stone එකකින් ගහද්දි බිත්තියට damage එක කළේ කවුද? mass එක. එහෙනම් ඒකේ meaning එක මොකද්ද? mass එක high වුණත් ඒක ගිහින් කොහේ හරි collide වෙච්චාම damage එක වැඩි. velocity එක high වුණත් ඒක ගිහින් කොහේ හරි collide වෙච්චාම එතෙන්ද damage එක වැඩි. එහෙනම් momentum එක කියන්නේ mass into velocity. mass එකයි velocity එකයි. මේ දෙක කොයි පැත්තෙන් ආවත් කරන damage එක වැඩි. එහෙනම් mass into velocity. මේ දෙකනේ මේ momentum එකෙන් පෙන්නන්නේ. එහෙනම් ওই momentum එක high තියෙනකොට තමයි damage එක වැඩි. මේකේ momentum එක. හරි? mass එක අඩු වුණත් velocity එකෙන් හැදිලා 100 ආවා. stone එකේ momentum එක. mass එක වැඩි වුණත් velocity එක අඩු වෙලා ආයේ 100ම තමයි බැස්සේ. හැබැයි දෙන්නගෙම බිත්තියට හානි වෙනවා වැදුනහම. damage එක වැඩි. එහෙනම් momentum එක කියලා කියන්නේ ඔය ගිහිල්ලා මොකක් හරි කොහේ හරි වැදුනහම ඒ වදින surface එකට තියෙන damage එක වැඩි නම් වදින surface එකට තියෙන damage එක වැඩි නම් ඒ වැදිච්ච object එකේ sure පිටම momentum එක වැඩි. එක්ක velocity එක එක්ක mass එක දෙකෙන් එකක් වැඩි. ඉතින් mass into velocity නේ momentum කියන්නේ. momentum එක වැඩි. හරි? එහෙනම් momentum එකේ physical meaning එක තමයි ඒ certain momentum එක දරන object එක. කොහේ හරි ගිහිල්ලා වැදුනහම එතන damage එක වැඩි නම් ඒ වැදිලා තියෙන්නේ ලොකු momentum එකකින් ආපු කෙනෙක්. Okay? So this is the physical meaning of the momentum and this is the equational meaning of the momentum. Okay. Write the next topic. Write the next topic. The relation of momentum with Newton's second law. The next topic, the relation of momentum with the Newton's second law. The relation of momentum with the Newton's second law. Relation of momentum with the Newton's second law. Relation of momentum with the Newton's second law. Sorry, relation of momentum with the Newton's second law. Relation of momentum with the Newton's second law. Now, in Newton's second law, they say force is equal to mass into acceleration. In Newton's second law, they say force is equal to mass into acceleration. Now, force is equal to mass into acceleration. Mass is here. What do you mean by the acceleration? Acceleration is the final velocity subtracted. We have to subtract the initial velocity from the final velocity, v minus u over t. Acceleration is the final velocity minus initial velocity over t. Okay, so F equals to m v minus u over t. I'm multiplying t to this side. Okay, I'm multiplying t to this side. Ft is equal to mv minus mu. Ft is equal to mv minus mu. So what is this mv? What is this mv? Mass into final velocity. Mass into final velocity. It will give you the final momentum. Final momentum. So what is this mu? Mass into initial velocity. It will give you the initial momentum. It is the initial momentum. So what is this Ft? I'll explain it with time. Huh? Okay, I need to fill the note up to this. The relation of momentum with the Newton's second law. F equals ma. F is equal to mass into acceleration. Acceleration is the final velocity minus initial velocity over time. Cross multiply t. Ft equals mv minus mu. What is mv stand for? M, mass into v, final velocity. So m into v, it's the momentum. Mass into final velocity, it will be the final momentum. And after subtraction, here you have the factor mu. What is m? Mass. What is u? Initial velocity. So what will be it? Mass into initial velocity. It will be the initial momentum. So Ft is equal to force into time is equal to final momentum. And the difference between the final and initial momentums. I need up to this. Himing ඇවිල්ලා. Himing ඉඳගෙන. හරි? ලංකාවේ අවුරුද්දකට මෙඩිසින් යන්නේ ළමයි 1300යි. අවුරුද්දකට ඉංජිනේරින් යන්නේ ළමයි 1400යි. ෆිසිකල් සයන්සස් වලට එකතුව. ෆිසිකල් සයන්සස් වලට ඔක්කොම කැම්පස් ටිකේ එකතුව 2000 තියෙයි. බයෝ සයන්ස් වලට එකතුව 2000 තියෙයි. ඔය ටිකනේ considerably තියෙන්නේ. IT ඔක්කොම ටික එකතු කරලා කියන්නේ. තව ඒ වගේ මැද්ද තියෙන courses වලට 500 ගාන දාන්න. හරි? මේ ඉතින් engineering medicine දෙපැත්තෙන්මනේ. maths පැත්තෙන් ගත්තොත් එහෙම engineering 1400යි. අතරමැද්දේ courses වලට IT, Colombo IT, Morato IT එකතු කරත් උපරිම මැද්දේ. හරි? statistical courses ඔක්කොම ටික 500යි. physical science වලට 2000යි. බයෝ පැත්තෙන් බලමු. මෙඩිසින් 1300යි. අතරමැද්දේ courses නැතිත් තරම් කමන්නේ 250ක් දාමු. හරි? physical bio science වලට 2000ක් දාමු. ඔච්චරයි. හරි? English medium, සිංහල medium කියලා බෙදලා නෙමෙයි ගන්නෙ. එකට ගන්න. හරි? ඉතින් මේ ටික තමයි කතන්දරය. හරි? දැඩි සැලකිල්ලක් දක්වන්න වෙනවා ඉතින්. මේ කරන උත්සාහයේ තේරුමක් නැහැ ලෝකල් යුනිවර්සිටි එකකට ඉඳ ගන්න ප්ලෑන් කරේ නැත්තම්. හරි? Okay, relation of momentum with the Newton's second law. F equals ma is the Newton's second law. So F is equal to mass into velocity, mass into acceleration, acceleration v minus u over t, ft multiplication, me minus mu. So me is the final momentum, mu is the initial momentum. Okay, so here force into time, the factor F into t has become the momentum difference. Okay, later I will teach you that this factor is known by the impulse. Later, with time, I will teach you that this Ft factor is known as the physical quantity impulse. Now, it is not my, wait. Now, I'm not going to consider about this impulse. If the force is multiplied by time, it's a separate physical quantity. That's the impulse. But now I'm at the beginning of momentum lesson. So the next, now I'm not going to introduce this impulse. This is what I want to show you. This is what I want to show you. Now from Newton's second law, it is clear force into time is equal to the momentum difference. If the force is zero, if this F is zero, what will happen? If this F is zero, Ft multiplication will be zero. So zero is equal to final momentum subtracting the initial momentum. So if the force is zero, the momentum difference will be zero. If the force is zero, the momentum difference will be zero. If the momentum difference is zero, take this to the left side. Initial momentum is equal to final momentum. Final momentum. That is the thing that I am going to show you now. Relation of the momentum with the Newton's second law. From the Newton's second law, now we achieved the equation Ft equal to me minus mu. For this equation, there's a separate base related with the physical quantity impulse. Now I'm not at that point. I'm in another case. I'm giving you another point. Okay, Ft is equal to me minus mu. Force into time is equal to momentum difference. If the force acting on the object is zero, what will happen? Ft multiplication will be zero. So zero is equal to final momentum minus initial momentum. So take the initial momentum to the left side, then initial momentum is equal to the final momentum. If the force acting on a body is zero, it will not have a momentum difference. If the force acting on the body is zero, it will not have a momentum difference. If there is no force acting on a body, it will not change its momentum. If there is no force acting on the body, it will not change its momentum. That's a very important fact in physics. Okay? Before write down these two other steps, I need the star mark from the middle. Before writing down the other steps, I need the star mark from the point where I have stopped now. From here, write it with a very clear, with clearly write down it. Okay. If the force F is zero, if the force F is zero, look at the note. If the force F is zero, if the force F is zero, it is very clear. If the force F is zero, it is very clear that the momentum difference is also zero. 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 So we can conclude. So we can conclude. So we can conclude that the momentum will not change. that the momentum will not change if there's no any force, if there's no any external force, if there's no any external force acting on the, if there's no any external force acting on the considered object. If there's no any external force acting on the considered object. If there's no any external force acting on the considered object. Right. Now you can finish the other two steps. හරි අර අපිට සමහර සින්දු මතක තියෙන ජීවිතේ පොඩි පද හරි ඒ වගේ මතක තියාගන්න මෙන්න මේ පදය. If there's no any external force acting on object, momentum will not be changed. If there's no any external force acting on that object, there's no any momentum change gain. The momentum change is zero. Here you can see that clearly. ඒක physics වල throughout the subject ඒක හොඳට deeply තියන් ඉන්න. If there's no any external force acting on that object, momentum won't change. හරි Okay, so this is the situation. Now, scientists have developed this concept into a broad manner. So this is the beginning of this momentum conservation. What do you mean by conservation? Conservation stands for something that does not change. What do you mean by conservation? Conservation stands for something that does not change. So here you can see that momentum hasn't changed. So this is the initiative steps. But scientists have developed this concept to a broader manner. They have developed it widely. Okay, now I'm going to expand this theory to a larger scale. I need this sentence. Scientists have expanded this concept. Scientists have expanded this concept to system of objects. Scientists have expanded this concept to systems. Scientists have expanded this concept to systems having more than one mass. Scientists have expanded this concept. Scientists have expanded this concept to systems having more than one mass. More than one mass. And they have introduced it. They have introduced it as a separate law. As a separate law. And they have introduced it as a separate law. And they have introduced it as a separate law. Okay. හරි දැන් විනාඩියක් ඔය වෙච්ච වැඩ ටික කියව ගන්න. roughly බලලා හුස්මක් අරන් ලෑස්ති වෙන්න. කලබලයක් නැහැ. theory ඉගෙන ගන්න. හුස්මක් අරන් පොඩ්ඩක් බලලා ලෑස්ති වෙන්න මොකක්ද ඊළඟට කියන්න යනවද කියලා. විනාඩියක් ගන්න නිදහසේ. හුස්මක් අරගෙන බලන්න මොකක්ද උනේ කියලා. මම සමරයිස් කරලා ඊළඟට ස්ටෙප් එකට යනවා. හරි. දැන් අහගන්න හරිද කියලා මම කියන ටික. හොඳට අහගන්න. Momentum is the multiplication of mass into velocity. First fact. The second fact, as a physical meaning, it stands for the damage caused to a certain surface when the object with that certain momentum hits it. If the damage is high, it's due to the higher momentum, the physical meaning. Third thing, from Newton's third law, we can have idea about this momentum conservation. From Newton's third law, we can have an idea about this momentum conservation. F equals ma, F equals m, v minus u over t, cross multiplying t, ft equals me minus mu. So ft stands for momentum difference. If f is 0, ft multiplication is 0, causing the momentum difference 0. So if there's no any external force, momentum won't change. Not changing, it's the conservation. It's the conservation. So momentum will be conserved if there's no any external force. But I explained this thing using the Newton's second law for a certain single mass. Scientists have expanded this theory into system of masses. That's what I'm going to show you. Now, for a certain object, I can apply F equals ma, where m is the mass of that object. Listen carefully. For a certain object, I can apply F equals ma, where m is the mass of that object. And from F equals ma, I have gained Ft equals me minus mu. And if F is 0, mv minus mu is 0. That means momentum difference is 0. So the momentum is conserved. It's same if there's no any F. For what I showed you that I have shown it for a single mass. Now I'm telling you that scientists have expanded this theory for system of masses. Okay, see it like this. Sorry. Now there's a mass m1. There's a mass m1 with a velocity v1. This is moving to the right side. And there's a mass m2 with a velocity v2. And if v2 is smaller than v1, if v2 is smaller than v1, can you tell me what's going to happen next? There's a mass m1 with a velocity v1, mass m2 with a velocity v2, and this v2 is a smaller value. What will happen next? As v1 is high and v2 is less, after a certain time, this m1 will hit the m2. There will be a collision. Why? This is with a higher velocity, and the object in the motion in the front object, it's having a lesser velocity. So the m1 will hit the m2 from behind. Okay. So after a certain period, there will be a collision. After a certain period, there will be a collision. M1 and M2 will collide. After the collision, from your practical knowledge, what can you say? After the collision, from your practical knowledge, what can you say? M1, M2. They will move with separate velocities, V1 dash, V2 dash. It's the fair way that you have to take. After collision, the velocity might change. Ne? Velocity might change. So that's the fair method. You have to change the velocity. Okay. So this is the one. Mass m1 with the velocity v1. Mass m2 with the velocity v2. As the v2 is smaller, v1 will hit it from behind. And there's a collision. So this is before the collision. Before the collision. And this is the collision. And this is after the collision. This is after the collision. Okay. Now I'm going to show you how the momentum will be conserved in a system like this. What I said initially, I have shown you how the momentum is conserved, how the momentum is not changed for certain mass m when f is 0. Now I will show you how they have expanded this theory into a set of masses like this. Okay, I need you to draw this first. Mark it as example 1, and I want you to draw this system. This is a system of masses. You have two masses which are going to collide, and you have to understand what happens after the collision. So this is a system of masses. I'm going to show you how the scientists have expanded the conservation of momentum to a mass set of masses. Okay, you have to draw it. පුතේ මවිඳු මේ ස්පේස් එක කැම් එකේ සිංගල් ස්ක්‍රීන් එකේ තියෙනවද? shape. ඔගොල්ලෝ දන්නවා මේ යථාර්ථය, මමත් මේ යථාර්ථය දන්නවා. ඉංග්‍රීසි මීඩියම් ළමයින්ට තියෙනවා සබ්ජෙක්ට් එක හරියට ඉගෙන ගන්න සෝසස් නැති ප්‍රශ්නයක්. ඒක ඇත්තනේ. ඒක ඇත්ත. ඒක කවදා හරි දවසක මගේ ජීවිතේ මට පුළුවන් උපරිමයෙන් මම විසඳනවා. හරි? ඒකෙන් පුළුවන් නම් පුතාලා ප්‍රයෝජනයක් ගන්න. පුළුවන් නම් කියන්නේ ගන්න. ඇත්ත කතාව දැන් මගේ දරුවෝ කවදා හරි ඉංග්‍රීසි මීඩියම් එක කරන්නේ. එතකොට මම දන්නවනේ ඒක පසුබිම. ප්‍රශ්නයක් තියෙනවා. හරි ලැන්ග්වේජ් එක තිබ්බොත් සබ්ජෙක්ට් එක නැහැ, සබ්ජෙක්ට් එක තිබ්බොත් ලැන්ග්වේජ් එක නැහැ. මේ දෙක එක තැනකින් ගන්න බැරුව ළමයි මාර කරදරයක් විඳිනවා. ඒ යථාර්ථය අපි දන්නවා. හරි ඉතින් ළමයි අමාරුවෙන් කේක විදි වලට මේක විසඳනවා ෆිසික්ස් වල. හරි මගේ ජීවිතේ මට පුළුවන් උපරිමේ මම මේක ළමයින්ට එක තැනක හරියට විසඳ ගන්න පුළුවන් බෑග්ග්‍රවුන්ඩ් එකක් හදන එකත් හදනවා. මට ගොඩක් මහන්සි වෙන්න වෙයි මම මේක කරමින් ඉන්නේ. ඔයගොල්ලොත් මේකට එකතු වෙලා පරිම සටනකින් මේක කරන්න බැරි දෙයක් නෙමෙයි. හරි ඊළඟ එකනේ papers ලියන්න sources නැති එක. ඒකත් ලෙහලානේ තියෙන්නේ. හරි ඒක ඉගෙන ගන්න ඕනේ, ලැන්ග්වේජ් එක ඕනේ, සබ්ජෙක්ට් එක ඕනේ, ඊළඟට papers ලියන්න ඕනේ. ලෙහලානේ තියෙන්නේ. දැන් තියෙන්නේ මේක කොහොම හරි අල්ලගෙන proceed කරන්න. ලොකු ශක්තියකින් මේකට මුහුණ දෙන්න. හරි මමත් කොහොම හරි ඒක කරනවා, පුතත් ඒක කොහොම හරි කරන්න. ඒක ඔයාගේ රිසල්ට් එක හොඳ වෙනවා. ඒක තමයි අපි දෙන්නගෙම growth එක. Okay. Now I have shown you how the momentum is conserved when the F is 0 for a single mass. I used the Newton's second law. Then I told you that they have developed this theory into a theory to apply when there are more masses than one. So here I have taken an example. I have these two masses, m1 and m2, and I have a incident, a collision. Before the collision, they are having velocities v1 and v2, and as the object velocity of the object that is in the behind, as it's a higher value, they will collide each other. After the collision, in our general knowledge, we know that the velocities will be changed. v1 into v1 dash, v2 into v2 dash. Okay, I'll show you how this conservation of momentum is applied into a situation like this. Okay, now from the Newton's second law, we saw that for the momentum to be conserved, for the momentum to be remain same without a change, F should be 0. F should be 0. From the earlier case, from analyzing F equals ma, we saw that momentum to be conserved, you need a special fact, the F should be 0. So even the single mass is considered, that's true. Even though you are considering set of masses, that's very true. So if the momentum is conserved, there the F should be 0. F is the external resultant force. It should be 0. So this should be if I am applying the conservation of momentum to the right side in the horizontal plane, in this horizontal plane, if I am going to apply the conservation of momentum, horizontal forces should be 0. So this should be a smooth surface. This should be a smooth surface. If there's friction, there are external forces, but you have an idea. For the momentum to be conserved, F should be 0. There should be no any F. So if there's a friction, there will be a frictional force acting on the object. So it's not good. Okay. Now write a small star mark from here. Write a small star mark from here. For the momentum to be conserved, 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 the external force, should be 0. For the momentum to be conserved, the external force should be 0. For the momentum to be conserved, the external force should be 0. So this should be a smooth surface. So this should be a smooth surface without frictional forces. So this should be a smooth surface without frictional forces. So this should be a smooth surface without frictional forces. Without frictional forces. And again, okay, keep it there and come to the board again. And again, let's finish it after this explanation. And again, now look at when this collision happens, when this collision happens, so these two objects are touching each other. When this collision occurs, these two objects are touching each other. When they touch, what happens? There's a normal reaction force created. When they are touching each other, definitely there will be a normal reaction force. So you will tell me, sir, how can you say F is 0? Even the friction is 0. Don't say F is 0. Why? When these two objects are touching, there's a normal reaction created. But I will answer you like this. Puta, yes, there's a normal reaction created. But again, there's a Newton's third law companion. So there are two normal reactions. They will simplify each other. They will cancel out. I was telling you that to momentum to be conserved, you saw from Newton's law, F should be 0. So to help that, I have write a sentence here that this surface is smooth without any frictional forces. Why? I need to be F to be 0 for my conservation of momentum. Now you are arguing back. Okay, friction is 0, but there's another force. Why? When they touch each other, when they collide, there's a normal reaction force created. So what about that? Pute, we are considering the system. When we consider the system, there are two normal reactions. Newton's third law couple is there. One creates a normal reaction on the second, and as well as a normal reaction to the opposite side as the Newton's third law companion. So there are two normal reactions. They will cancel out. Okay. Now complete the sentence. And again, the forces created at the collision. And again, forces created at the collision. Let's complete the sentence that we were writing. And again, the forces creating, and again, the forces, created at the collision. And again, the forces created at the collision are also cancelled, when we consider the system. When we consider the system. Okay. Now take your red pen and draw these forces and simplify them. Take your red pen and draw these forces and simplify them. Okay. Now I'm showing you the most important case now. Okay. Look at the board again. Now from the previous case, I have given you a fact that the momentum is conserved when there's no any F. To help that fact, now I am giving you some additional facts. Now there's a system of masses m1 and m2 in a motion. So there are momentums. Let's check whether the momentum is conserved. From the initial case, F equals ma, we have shown that F should be 0 for the momentum to be conserved. So I'm trying to get a 0 F condition here. What are the forces acting on these objects? Frictional forces might be there. If I select a smooth surface, no frictional forces. And again, what are the forces that might acting on these objects? When they collide each other, there are normal reactions. But when you consider the system, there are two reactions in the opposite direction from Newton's third law. So they will cancel out, no problem. And again, listen, here as this is a M1, you have this weight M1G. And when it touches the ground, you have this normal reaction R from the ground. So they are external forces. So remember, for a system like this, you can't consider the conservation of momentum to the vertical direction. Why? The weight and the normal reaction is present. Can take your pencil and can you draw these two forces? As here, it has this weight M1G. Take your pencil and draw this thing. Here, for the mass M1, it has its weight M1G. And again, when it touches the ground, there's a normal reaction. Again, when it touches the ground, there's a normal reaction. So these are the external forces. So what we do about that? What we can do about that? There's M1G and R here. Draw them in using a pencil. Okay. Now come to my next star mark. Even though the friction and R is even though the friction is neglected through a smooth surface, even though the friction is neglected through a smooth surface, smooth surface, and R is neglected, even though the friction is neglected through a smooth surface and the R is neglected, as it cancels with the Newton's third law companion, and R is neglected as it cancels with the Newton's third law companion, still weights and the normal reaction from the ground, still the weights and the normal reaction from the ground, still the weights M1G and the normal reaction from the ground R, still the weights M1G and the normal reaction from the ground are present. So let's consider the horizontal direction. So let's consider the horizontal direction where M1G and R, are not effective. Where M1G and R are not effective as they are perpendicular. Vectors to the horizontal. As they are perpendicular vectors to the horizontal. As they are perpendicular vectors to the horizontal. Okay. As they are perpendicular vectors to the horizontal. Okay. Now listen again. Now listen again. Momentum is the mass into velocity multiplication. From F equals ma, it is clear that the momentum is same. It won't change if F is 0. I have shown it to you for a single mass using F equals ma equation. They have expanded this theory to a set of masses like this. Now I am going to show you how to consider the momentum conservation to a system of masses more than one, m1, m2. Now, for that also, the first fact you have to understand, to apply this conservation of momentum, the external force F should be 0. So when these objects are moving, there might be external force called friction due to the surface. I considered the smooth surface, so I don't need to worry about the friction. Even though I have neglected the friction through the smooth surface concept, still there's a normal reaction force acting on each other when they are colliding due to the collision, when they are touching. As it is created as a pair, when we consider the system, both of them will cancel out, equal and opposite. So that problem was also solved. Still there's a problem. The weight M1G is there, M2G is there, and there are normal reactions when they touch the ground. But I can neglect these two forces if I consider the horizontal. Why? These M1G and R are vertical. Verticals will not affect the horizontal. So I am considering the horizontal. So I will write something like this. Apply conservation of linear momentum. Applying conservation of linear momentum horizontally to the front direction. Okay. So I'm writing a phrase like this: applying conservation of linear momentum horizontally to the front direction. As I'm applying the conservation of linear momentum horizontally, I don't need to worry about the vertical forces. Why? If there's no any conservation of momentum, but still I'm using the horizontal, so the vertical forces will not affect. And I'm on a smooth surface, so the friction will not affect. And I'm considering the system of masses, so R's will cancel out. Okay, so this is my conservation of linear momentum. Now, before the collision, I have m1 with the velocity v1. So m1 v1 is that certain momentum. Before the look at the board, before the collision, I have a m1 with the velocity v1. So the momentum is m1 v1. And from here, I have a momentum m2 v2, mass m2, velocity v2. So these are the initial momentums. Here m1 into v1 and m2 into v2. So these are the initial momentums. They are equal to final momentums. m1 into v1 dash from here. What is the other? m2 into v2 dash. m2 into v2 dash. So this is the conservation of momentum to a system of masses. To apply the conservation of momentum for a single mass or system of mass in the considered direction, if the external force should be 0 through a smooth surface, and by considering the complete system to cancel out R's and considering the horizontal direction, leaving the verticals behind, I have gained a system with the 0F to the considered horizontal direction. So the momentum should be conserved as they say. So what are the momentum parts? M1 into V1, M2 into V2. They are equal to final momentum parts, M1 V1 dash, M2 V2 dash. So this is how it goes. Okay, you can complete it now. This is the conservation of linear momentum for system of masses. Initially, they saw this through F equals ma for single mass, and they have expanded to a situation like this. When there is a set of masses in a system, you can apply the conservation of momentum like this. F should be 0. If so, the initial momentum parts will be equal to the final momentum parts. It's conserved, the momentum. කවිරුත් නිකන් කතා අහගෙන ඉන්නවා වගේ මට පේනවා මගේ හොඳ ළමයා කවිරුත් උත් එක අහගෙන ඉන්නවා අනිත් කෙනෙක් කතා කරනවා මොකද මේ ඊයේ පහමාර 5:45 වුණා පන්ති හරි මෙතනට නම් කොල්ල විතරයි නේ ගහන්නේ ඊයේ කෙල්ලෙක් කියනවා ගෙදර යන්න ඕනේ කියලා හරි ඊළුවට හරි දැන් ගෙදර ගිහිල්ලා මේ හදන නෝට් එක කියවන්න ඕනේ දැන් මේ ප්‍රසන්ට් මේ සිටුේෂන් එකේ දැන් මේ ඔයා නෝට් එක බිල්ඩ් අප් කරගෙන ඉන්නේ ඊට වඩා දෙයක් පේනවා මේක කම්ප්ලීට්ලි අරන් බැලුවා ඒ නිසා ගෙදර ගිහිල්ලා අනිවාර්යෙන් කියවන්න ඕනේ මේ හදලා ගැදර් කරගන්න පොයින්ට්ස් ටික එතකොට තමයි මේ ෆුල් පික්චර් එක පේන්නේ දැන් තාම ඔයා සිටුේෂන් එකට මුණ දෙනවනේ නෝට් ලියනවා එහෙම මෙහෙම බලනවා අහගන්නවා තාම මැදනේ මේක තමන් කන්ක්ලූෂන් එකකට එන්නේ ගෙදර ගිහිල්ලා මේ ෆුල් ස්ටෝරි එක ආයෙ කියවන්න ඕනේ එතකොට තියෙයි කම්ප්ලීට් පික්චර් එකක් වැඩේ වෙන විදිහකට හරි ඒ කම්ප්ලීට් පික්චර් එක අවශ්‍යයි මොකද කල් යද්දි මේව අමතක වෙනවා ඒකට ආයෙ බලා ගන්න තැනක් තියෙන්න ඕනේ හරි ගෙදර ගිහලා අනිවාර්යෙන්ම බලන්න හරි so this is how you are applying the conservation of linear momentum okay before solving the questions I'm going to explain it again and going to give you this as a rule I will tell you the story again and then I will give this diagram as a single rule in physics. Okay. බලා ගන්න එහෙනම්. මෙන්න මේකයි සීන් එක. මොමන්ටම් එක කියලා කියන්නේ mass into velocity multiplication එක. measure කරන්නේ kg meters per second වලින්. මොමන්ටම් එකේ ෆිසිකල් මීනින් එක ඒ මොමන්ටම් එක තියෙන ඔබ්ජෙක්ට් එක කොහේ හරි ගිහිල්ලා වැදුනහම ඒ කෝස් වෙන ඩැමේජ් එකේ ප්‍රමාණය වෙලොසිටි එක පැත්තෙන් උනත් ඩැමේජ් වෙනවා බෝල් එකට මතකද මෑස් එක පැත්තෙන් උනත් ඩැමේජ් වෙනවා ඒ කියන්නේ මොමන්ටම් එක මොකද මෑස් ඉන්ටු වෙලොසිටි වල ඉන්නේ මොමන්ටම් එක ස්කෑන් කරන්නේ ඒක ඊට පස්සේ මේ මොමන්ටම් එකයි F equals ma අතර තියෙන රිලේෂන්ෂිප් එක F equals ma F equals v minus u over t F equals m v minus u over t ft equals me minus mu So ft is the impulse. I'll take it later. Now let's continue. Ft is equal to me minus mu. So f is 0. Ft multiplication 0. 0 is equal to mv. Final momentum minus initial momentum mu. So if f is 0, momentums are same. Momentum is conserved. It won't change. So it's for a single mass. They are from f equals ma equation for the single mass called m. Scientists have expanded this theory to set of masses. Even you are considering a single mass or a set of masses, there's a very important thing that you have to pay your attention. Momentum will be conserved only if external force acting on the system is 0. So I took a smooth surface where there are no any frictions. And again, there was a problem for me about these two R's when that occurs when the collision is there. But when we consider the system, there are two R's with equal and opposite values from Newton's third law, so they will cancel out. That problem is also solved. And again, there's a very heavy problem. How can we say that F is 0? There are weights, normal reactions from the ground. But if I consider the horizontal, these normal weight and the normal reaction are vertical. Verticals will not affect the horizontal. That is also solved. So now I am applying the conservation of linear momentum horizontally to the front direction. I don't have any external force in this system to the horizontal front direction. These are vertical. Friction is neglected. These are cancelled. So I can, as they say, I can apply conservation of linear momentum horizontally. Okay. So there's here you have a set of masses. So you have to consider all the momentum parts from each and every mass. This one M1 velocity V1, momentum part M1 V1. This one M2 velocity V2, momentum part M2 V2. So these are the initial momentums. If it is conserved, they are equal to the final momentums. What are final momentums? M1 V1 dash, M2 V2 dash. Okay, so this is the situation. Now I will give you whole thing as a single rule from a sentence. Take the red pen and write down the rule down. I will give you all the things contained in this diagram from a single rule. If there are no any external forces, if there are no any from red pen, if there are no any external forces, 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 if there are no any external forces acting on a system, if there are no any external forces acting on a system to a considered direction, if there are no any external forces acting on a system to a considered direction, if there are no any external forces acting on a system to a considered direction, the momentum of the system, the momentum of the system, the momentum of the system will be conserved, will be conserved towards that direction. Momentum of the system will be conserved towards that direction. Momentum of the system will be conserved towards that direction. Momentum of the system will be conserved towards that direction. Okay. Now go to your tube and let's solve the first 3 questions. Go to your tube and let's solve the first 3 questions. AC එක වැඩි කරලා දෙන්න. දැන් ටෙම්පරේචර් එකට මොකද කරන්නේ? වැඩි කරලා දෙන්න. තව කොහොමද වැඩි කරන්නේ? පුතේ භවිතු මෙතන AC එක පොඩ්ඩක් අඩු කරමු. අඩු කියන්නේ උෂ්ණත්වය වැඩි කරලා පිල්ලමු. පිරිමි ළමයින්ට නම් මේක මදි. දැඩි සීතල අවශ්‍යයි. අනිත් එකෙන් අපි අර පිටිපස්සෙන් අඩු කරමු ඒකට. වහලා හරි. පළවෙනි ක්වෙස්චන් තුනද මේ පැත්ත අඩු කරමු නේ. හරි. හරි. පිටිපස්සෙන් අඩු කරමු. පිටිපස්සෙන් පූල් එක වැඩි කරමු ඈ. අපි ජීවිතවල කොච්චර දේවල් දන්නේ නැද්ද කියලා කියන්නේ මම මේ කියන්නේ මගේ විශ්වවිද්‍යාල කාලේ කතාවක්. හරි? මිනිස්සු මේ ලෝකේ ගැන කොච්චර දන්නවද? අපි කොච්චර ටිකද දන්නේ කියලා උදාහරණයක්. කැම්පස් එකේ අපේ ඇමරිකාවේ ගිය අයියලා. ඉතින් අපිත් ඒ කාලේ වෙනකොට දැනගන්නේ. ඉතින් අපි නොදන්නවා කියන එක නෙමෙයි. අපිත් ඒ සමාජයත් එක්ක ගැටෙනකොට දැනගන්නේ. ඉතින් PhD එකට යන අයියලාට එහෙ PhD එකට ගිහින් ඉන්න අයියලා දීප උපදේශක් ඇමරිකාව ලොකු රටක් නේ. ඇමරිකාවේ සමහර පැති තියෙනවා ලංකාවේ වෙදයකට කිට්ටු එකේ. ඒකට ඒවා සිලෙක්ට් කරන්න කියන්නේ. කොහොමද ඒක? ඇමරිකාව ලොකු රටක් නේ. මේ ලොකු මේකක පැතිරිලා තියෙනවානේ. ඇමරිකාවේ සමහර පැති තියෙනවලු. ඒවායේ වෙදයක මේ මෙහෙට වඩා ගොඩක් වෙනස් නෑ. එන්නටම මයිනස් එකක් නැති හැම කාලෙම. සමහර කාලවල මයිනස් ගියත් ගොඩක් කාලවල ලංකාවේ වෙදයකට සමානයි. ඒතර PhD එකට එහෙම පැති සිලෙක්ට් කරන්න කියලා. ඒතර Tamanට වෙදයකින් කරදරේ අඩු නිසා. බලන්න කොච්චර පුංචි දේවල් වුණත් ඒවා හරි ඉෆෙක්ටිව් නේ ඉතින්. නේ? ගිහිල්ලා අවුරුද්දම සීතලේ ඉඳගෙන PhD කරන්න බෑනේ. ටික කාලයක් හරි ලංකාව වගේ තියෙනවා නම් ඒකනේ අපේ ඇඟට හුරු. ඉතින් එහෙම පුංචි ෆැක්ට්ස් කොච්චර තියෙනවද ජීවිතවල අපි ලෝකේ ගැන දැනගන්නනේ. ඔහේ කරන්නම් වාලේ දෙයක් කරන්න නැතුව ඊළඟට දැන් ඇමරිකාවේ දැන් මේ ට්‍රම්ප් ගොඩක් වෙලාවට පාරවල් වහගෙන නැන්නේ පිටරටවල ස්ටුඩන්ට්ස්ලාට. බෑ මතක තියාගන්න ජර්මන් වල හරි ජර්මන් කියන්නේ ලෝකේ තාක්ෂණයේ ගොඩාක් උඩ ඉන්න රටක්. හරි ඒගොල්ලෝගේ BMW Volkswagen ඔක්කොම යාළගෙන. ජර්මන් වලත් මාර PhD opportunities ටිකක් තියෙනවා. ප්‍රශ්නේ තියෙන්නේ ඒ වැඩි ඒගොල්ලෝ ජර්මන් ලැන්ග්වේජ් එකත් ටිකක් පුළුවන්ද කියලා බලනවා. ගොඩක් නෙමෙයි ටිකක්. ඉතින් කැම්පස් එකකට යන කාලෙක ඔය ගොඩාක් යන ෆැකල්ටිස් වල ආර්ට් ෆැකල්ටිස් එහෙමත් තියෙනවා. ඉතින් අපි ගිහිල්ලා සයන්ස් එකේ ඉන්න ගමන් රික්වෙස්ට් කරොත් ආර්ට් එකේ ලැන්ග්වේජ් කෝස් එකකට අනේ කවදාකවත් එපා කියන්නේ නැහැ. අපි ගිහිල්ලා ජර්මන් ලැන්ග්වේජ් එක කරන ලෙක්චරර්ට කියනවා මම සයන්ස් කරන්නේ. මගේ ටාගට් එකක් තියෙනවා PhD එකට ජර්මනුත් ඇප්ලයි කරන්න අනික් ඒවා අතරේ. සමන් ජර්මන් ලෙක්චර් එකට එන්නද? වාහිතව දෙපා කියයි කියලා. කතා කරලා ගන්නෙ. ලෙක්චර් එකෙත් පෙන්නයි ආර්ට් කරන සෙට් එකට මේ සයන්ස් එකේ කොල්ලෙක් ඇවිල්ලා ඉන්නවා මරු පුතෙක් කියලා. හරි නිකන් ගිහිල්ලා අහන් හිටියනම් මොකද මේ ජර්මන් ගත්කතුවරයෙක් වෙන්න නෙමෙයි. පොඩි නොලෙජ් එකක් නේ ඕනේ. ඒක ඇප්ලයි කර හැකිනේ. අර මේ ඇප්ලිකේෂන් එකේ කිව්ව හැකිනේ මෙහෙම නොලෙජ් එකක් තියෙනවා මට කියලා. හරි. ඉතින් ඇමරිකාවේ අවස්ථාවල් වැහෙනවා. බටහිර යුරෝපය ආශ්‍රිතව තියෙන මේ ලැන්ග්වේජස් පොඩ්ඩක් මේ හින්න ෆ්ලුවන්ට් වෙන්න නෙමෙයි. ඉංග්‍රීසි නොවන යුරෝපයේ තියෙන අනික් ලැන්ග්වේජස්. දියුණු රටවල පොඩ්ඩක් ගොඩ දාගන්න පුළුවන්. විශ්වවිද්‍යාලයක ඉන්න කාලෙම නේද? මොන දේවල් ජීවිතවල අපේ අවස්ථාව කොහොමද හදාගන්න වෙන්නේ කියන එක බලන්න. ඉතින් හැබැයි ඉතින් මොනවා කරන්න මේ වෙලාවේ මුකුත් කරන්න බෑ. මේක ඉවර කරන් ඉන්න ඕනේ. පස්සේ කාලෙක විශ්වවිද්‍යාලයකදී කරන්න පුළුවන් වැඩ. ලෝකෙ ලොකුයි. මුළු ලෝකෙම තියෙන opportunities වැහෙනවා කියලා කියන්න බෑ. හරි තැන හොයාගන්න අපිට දක්ෂ වෙන්න. අනික ඉතින් දැන් තාම හැමදාම ඉන්න එකකුත් නෑ. Okay, let's go to the first question. කොහොම නමුත් එකක් පැහැදිලි. ඉස්සෙල්ලා A level හොඳට කරගත්තොත් ඉස්සෙල්ලා A level හොඳටම සුපිරියර්ට කරගත්තොත් ලොකු ලෝකයක් තියෙනවා අඩිය තියාගන්න. ඒක ලංකාවේ ලෝකල් යුනිවර්සිටි එකක් නෙමෙයි වුණා. ඒකට opportunities නැතුව නෙමෙයිනේ එළියේ. මොකක්ම හරි මැච් එකක් ගහක හැකි මේක ගොඩ දැම්මා. එතනදී එක වටින දෙයක් තමයි ලංකාවේ A level ලෝකෙ පිළිගන්නවා. දැන් සමහර රටවල් තියෙනවා ඔයා හිතන්නකෝ ඔයා උගන්ඩාවේ A level කරා කියලා. නැත්තම් ගිහිල්ලා ජිබුටියට ගිහිල්ලා A level කරා කියලා. බලු බල්ලෙක් ගණන් ගන්නෑ. හැබැයි ලංකාවේ A level කරා නම් ගණන් ගන්නවා. ලෝකේ හැමතැනක්ම ගණන් ගන්නවා. මොකද ලංකාවේ A level විභාගයේ තියෙන ස්ටෑන්ඩඩ් එක ඒගොල්ලෝ දන්නවා. ඒ ලංකාවේ A level කියන එක මේ ලෝකේ තියෙන ලොකු ක්වොලිෆිකේෂන් එකක්. ඒ වගේම ලංකාවේ විශ්වවිද්‍යාලයක උපාධිය කියන එකත් ලෝකෙ පුරා පිළිගන්න ක්වොලිෆිකේෂන්. මොකද ලංකාවේ තියෙන අධ්‍යාපන තරගෙත් එක්ක පොඩ්ඩ දෙනාටනේ ඇතුල් වෙන්න පුළුවන්. එළවලුත් ඒකනේ. ඒ නිසා ඒක ලෝකේ දන්නවා. ධම්ම විභාගයක් කියලා. අපිට සෝසර්ස් නෑ අපේ ජීවිතවල ප්‍රශ්න මෙහෙ තියෙනවා. ඒ ඔක්කොම හරි. මේ විභාග ඉන්ටර්නැෂනලි ඇක්සෙප්ටඩ්. දැන් මේක ගොඩ දාන එක තමයි මේකේ ෆස්ට්ම වැඩේ. හරි. නැති පැත්තෙන් කතා කරනවට වඩා පොසිටිව් පැත්තෙන් කතා කළොත් මේක ලොකු වාසනාවක් මෙහෙම විභාගයක් තියෙන රටක ඉන්නේ. මොකද මේක ගොඩ දැම්මොත් ලෝක පිළිගැනීමක් එනවා. Okay. The first question, a body A, the body A of mass 10 kg, a body A of mass 10 kg is moving on a smooth horizontal surface with a velocity of 5 meters per second. A body A with a mass of 10 kg is moving with a velocity of 5 meters per second in a smooth horizontal surface and hits a body B. The weight of the body B is 4 kilograms, and the velocity of it is 2 meters per second. Now it's very clear B is having the lesser velocity. So what will happen? A will collide with B after a certain period. As A is having the higher velocity, A will collide B from behind. There are no any frictional forces as this is a smooth surface, and when they collide to each other, they are touching each other. So there are normal reactions created, but there are two of them to the opposite direction. So they will cancel out when you consider the system. And after that, after the collision, they will move with changed new velocities, v1 dash and v2 dash. There, after the collision, it is observed that the velocity of A becomes 1 meter per second. Velocity of A is equal to 1 meter per second. So what will be the new velocity for B? So what will be the new velocity for B? Okay. You have to write it here. Put in A-level marking scheme. There's a mark for this thing. You have to show the direction and you have to say apply linear momentum conservation. Apply linear momentum conservation. You have to say it. And from the arrow, you can say the direction that you are applying. I'm going to apply the linear momentum conservation horizontally to the forward direction, to the right. I'm going to apply the linear momentum conservation horizontally to the forward direction. Horizontal and forward. I can denote it by this arrow. But I have to write, at least I have to write this thing. Apply linear momentum conservation. To apply the linear momentum conservation to a certain direction, the resultant force on that direction should be 0. Is it okay here? Yes, no frictions. R are cancelled. And weight and the normal reactions on the ground, they are vertical. They will not affect the horizontal. So freely I can apply the momentum conservation to the right direction in the horizontal. So I have to consider the initial momentums. Mass 10, velocity 5. Mass 4, velocity 2. As the momentum is conserved, these two values should be equal to the final momentums. Mass 10, velocity 1. Mass 10, velocity 1. And mass 4, velocity v2 dash. Mass 4, velocity v2 dash. 58 is equal to 4. 58 is equal to 10 plus 4 v2 dash. 48 is equal to 4 V2 dash 12 is equal to V2 dash 12 meters per second. So the new velocity of the object with a mass 4 kg, object B, is having a new velocity of 12 meters per second. We got that from the conservation of linear momentum. Okay, go to the second question. Now I am giving you a set of questions 1, 2, 3, 5, 8, 10. 1, 2, 3, 5, 8, 10. 1, 2, 3, 5, 8, 10. A body of mass 6 kg, a body of mass 6 kg, second question, moves on a smooth horizontal surface with a velocity of 4 meters per second. And another body of mass 2 kg, another body of mass 2 kg, moving in the same direction with a velocity of 3 meters per second. They collide with each other. After the collision, they will start to move from new velocities. Velocity of A will become a value 2 meters per second. And find the new velocity of B, V2 dash. I can apply the conservation of linear momentum to the horizontal direction, where the normal reaction from the ground, they are vertical. Horizontally, if there are forces, they should be the friction and the forces due to the collision. But the forces due to the collision are neglected as there are two, and both of them will cancel out as they are equal from value from Newton's third law. And as I considered a smooth surface, no harm from friction. So I can freely apply linear momentum conservation to the horizontal direction. I have to write it. Linear momentum conservation, and from arrow I can indicate the direction horizontally rightwards. So the momentum is conserved horizontally rightwards. Okay, what are the initial momentum parts? 6 into 4 plus 2 into 3 will be equal to the final momentum parts. 6 into 2 plus 2 into V2 dash. 10, 6, 12, 2 V2 dash. Okay, 64, 2. 2 meters per second is the velocity I got. I think there's a body of mass 6 kg moves on a horizontal surface with a velocity of 4 meters per second. Another body of B is mass 2 kg moving with a direction of velocity of 3 meters per second. After the collision, the velocity of A becomes 2. And what is the velocity of B? 6 into 4, 2 into 3. Here, 6 into 4 is 24. 30, 30, 18, 9. I got the answer. 9 meters per second. Okay, move to the third one. Now, little by little, now we are gradually increasing the weight of the question. Now, these are very simple questions at the beginning to make you practice with the theory, and gradually we have to go for higher questions. Okay. After the 10th one, let's continue with the 12 and then question number 14. The stand of these questions will increase in this ascending order. Then 15, 16, 17, 18, 19. 16, 17, 18, 19. Now pass කරගෙන ඉස්සරහටම යන්න. හරි. Okay. 1, 2, 3, 4, sorry, 1, 2, 3, 5, 8, 10, 12, 14, 16, 17, 18, 19. One, two, three, 5, 8, 10. 1, 2, 3, 5, 8, 10. 12, 14, 16. 12, 14, 16, 17, 18, 19. Okay. The third one. Third question. On a smooth horizontal road, there's a 200 kg vehicle with a velocity of 10 kilometers per hour. It collides with the stationary 300 kg vehicle. It collides with the stationary 300 kg vehicle. That means a vehicle with a zero velocity. And at the collision, there will be normal reactions created in the touching surfaces. But when we consider the system, they will cancel out. As this is a smooth road, no need of worrying about the friction. And after the collision, there's a special thing happened. Both of them are moving as a single object. These things can happen. After the collision, both of them are moving as a single object with 500 kilograms. These things can happen. Not always, but it's possible. That's a probability. After the collision, they are moving as a single object. They are touched each other throughout the motion. They are not separating. They are in touch with each other and moving straight. Let's say their common velocity is v. So there are no any external forces in the horizontal direction. So applying linear momentum conservation, LMC, linear momentum conservation, LMC, to the horizontal, applying LMC, linear momentum conservation, rightwards, horizontal. This is the shortened form. Okay. So what are the linear momentums at the beginning? 200 into 10, 300 into 0 is equal to, after the collision, they are moving as a system. So the mass is 500. The mass together, 500 into V. Both of them are moving, keeping in touch with each other. So the complete mass is 500, common velocity is V. So the momentum 500 V after the collision. So I can simplify it. 300 into 0, no value, it's 0. It's 20, 5V. So after the collision, the system is moving with a common velocity as a single mass with a 500 kg value, and the velocity of it, we got it as 4 kilometers per hour. Okay, go to the fifth question. Go to the fifth question. Question number 5. A bullet of mass 25 g a bullet of mass 25 g fired horizontally into a wooden block of 475 grams. There's a wooden block with a mass of 475 grams. A bullet of 25 g is fired towards that block with a velocity u. And what will happen? The bullet will penetrate the wooden block and it will stop inside. Due to the engagement of the bullet, the system, the bullet and the wooden block will move front. Will be moving to the front direction with a velocity of 5 meters per second, with a common velocity of 5 meters per second. If this is the case, you are asked to find the initial velocity of the bullet. You are asked to find the initial velocity of the bullet. Now, when the bullet is coming towards the wooden block, if we consider the horizontal direction, there are no any considerable external forces acting on the system. There might be frictions from the air, but they are negligible. When the bullet comes to the front direction to be collided with the block, there's a friction from air. I know that, but they are negligible. Weights, they are not negligible, but they are vertical. They will not affect the horizontal. So as there are no any horizontal considerable forces acting on the system, I can apply LMC, linear momentum conservation, to the rightward direction horizontal. What are the initial momentums? 25/1000 into u, weight and the velocity of the bullet will give you mass, and the velocity of the bullet will give you the momentum of the bullet. And 475/1000 mass into velocity 0. Initially, the wooden block is at rest. So there's no any momentum component created by the wooden block at the beginning. It's the only bullet that creates the momentum. But after bullet penetrates the wooden block, both of them are a certain single system and they are moving at a velocity of 5 meters per second. Now they are compound weight 25 plus 475. 25 plus 475 over 1000 into 5. Total mass 500 grams. Velocity 5. 1000 will cancel out. 25u plus 0 is equal to 500 into 5. 25u is equal to 2500. So the velocity is equal to 100. From the conservation of linear momentum, we found that the bullet had the initial velocity of 100. Okay. Okay. Now move to 8th question. 8th question. පිටරටකට යනවා කියන ටාගට් එක තියෙනවා නම් ඒකට හොඳම තැන ගෙදර අයගේ සල්ලි ටික ඔක්කොම ටික ඉල්ලගෙන A level වලින් යන එකම නෙමෙයි. ඔක ඊට වඩා ලොකු තැනකින් කර හැකියි. කරන්න තියෙන ගැළපෙනම තැන තමයි යුනිවර්සිටි සිලෙක්ට් වෙලා යුනිවර්සිටි එකේ ෆයිනල් ඉයර් එකේ MSc එකකට හරි PhD එකකට හරි පිටරටකට ඇප්ලයි කරන්න එක. ස්කෝල් එකකට හරි සෙමි ස්කෝල් එකකට හරි. හරි. එතකොට ඔයාට පිටරට ගිහිල්ලා හම්බ වෙන ඒ educational opportunity එක A level වලින් යන එකට වඩා ගොඩාක් ලොකු එකක්. මොකද සුද්ධෝ දියුණු වෙලා හින්දා උන්ට සල්ලි තියෙන හින්දා ඒ රටවල් වල උන්ගේ දරුවෝ එහෙම ගොඩාක් ඉගෙන ගන්න. ඉගෙන නොගත්තත් උන්ට කාර් එකක් ගන්න පුළුවන් මාසයක් දෙකක් පඩියක් කරන්. ඒ නිසා උන්ට ලොකුවට දැනිලා නැහැ ඉගෙන ගන්න ඕනේ කියන එකනේ. දියුණු රටවල් වල. ඒ නිසා උන්ගේ අලුත් ජෙනරේෂන් එක ඉගෙන ගන්නවා අඩුයි ටිකක්. සාපේක්ෂව. ඒ නිසා ඒ opportunities ගන්න බෑ A level කරලා ගිහින්. ඒ opportunities ටික ගන්න වෙන්නේ යුනිවර්සිටි එකක ෆයිනල් එකකින් MSc එකකට ගිහිල්ලානේ. PhD එක. ඔන්න තැන. ඒක තමයි හොඳම තැන. ගෙදර තියෙන සල්ලි ඔක්කොම ටික අරගෙන ගියත් අපිට ඒක අමාරුයි A level වලින් ගිහිල්ලා පුළුවන්. නමුත් ඊට වඩා හොඳ තැනක් තියෙනවා පිට රටකට යන්න. higher education එකනේ. ඒකට මේක ගොඩ දාගන්න බැරි නෑ. හරි ඉතින් මේ වැඩේ මුළු හදවතින්ම මේ වෙලාවේ කරෙන්න ඕනේ. වෙන වැඩක් නෑ මේ වෙලාවේ. හරි. වෙලාවට එන්න ඕනේ. papers ලියන්න ඕනේ. හරි. නැත්තම් මේ වටිනා අවස්ථාව ගිලිහෙන්නේ. හරි. එතකොට 8 question number 8. Question number 8. A rocket moving in space. A rocket moving in space at 50 meters per second. A rocket is moving in the space with a 50 meters per second velocity. Explodes into two equal fragments. Let's say the initial mass is 2m. So it has exploded to two fragments with mass m. Why? The initial mass is 2m. So if it is exploded into two equal parts, m and m, if one fragment comes to rest immediately after the explosion, one fragment will have a zero velocity. After the explosion, one fragment will have a zero velocity. So you are asked to calculate the velocity of the other fragment. Okay. Now you are in the space. When you are in the space, the weight, the gravitational force is not there. And in the space, frictions are also very negligible. So without a problem, external forces are zero. If you consider any external force, this is the only thing that you have to worry. When there is an explosion, there might be forces created on each and every part from the explosion. But all the forces have a Newton's third law companion, so these forces will also cancel. Listen to this thing, not only the equation, theoretical background. For the momentum conservation to be applied, the external force in that certain direction should be zero. Now you are in the space, so there's no any gravitational force from Earth, no weight. You are in space, so that is solved. And in the space, friction is also negligible, so you don't need to worry about the friction. But still, from the when it explodes, when it explodes, there are forces created on every and each fragment. But in that case, always there's a Newton's third law companion to a force, so they will cancel out when you consider the complete system. You apply the conservation of linear momentum to the system, not for a single fragment. As you are applying it to the system, you have to consider the whole system. When you consider the whole system, Newton's third law companions will cancel out related with the forces at the explosion. Okay, no friction and no weight in the space. Forces due to the explosion will cancel out each other as you are considering the complete system. So you can apply the linear momentum conservation LMC to the preferred direction, to the initial direction that the rocket is moving. Applying LMC to the initial direction. Applying LMC to the initial direction. When you are applying LMC to the initial direction, what is the initial momentum to the certain direction, to the consider direction. Let's say mass is 2m, velocity is 50. So the initial momentum is 2m into 50. And after the explosion, there are two fragments, one with the mass m, but suddenly it stops. So the momentum 0, m into 0. It doesn't have a velocity after the explosion, m into 0. Other part, it's also m with a velocity v2 dash. What has happened? 100 m is equal to mv2 dash. M is the factor we considered to explain the mass. It cancels. So v2 dash. The remaining fragment will start to move with the velocity of 100 meters per second. Okay. Now go to the 10th question. Go to the 10th question. At the end of the tube, you will meet very difficult questions. Okay. But first, you have to go through basic questions in order to understand the theory in a proper manner. And questions will be developed in the ascending order. And when you reach question number 25 or 26 or 30, you can take the real experience from there. But before that, you have to go in this order. Okay, question number 10. Question number 10. A spacecraft of mass 50 kg. A spacecraft of mass 50 kg moving in space with a velocity of 100 meters per second. It explodes into two equal fragments. Let's say the mass 50. So the fragments will have masses of 25 kg each. One fragment moves at a velocity of 30 meters per second. And it moves to the opposite direction. That's the fact here. After the explosion, one fragment moves to the opposite direction from the opposite direction when you consider the initial direction. And you are asked to find the fragment, the velocity of the other fragment, v. Applying LMC to the initial direction. Here, you are in the space. Now, in the 10th question, you are in the space. In the space, there's no weight. Gravitational force is not there. So, you don't need to apply the equation horizontally. Horizontal or whatever, no problem. Weight is not there. Or normal reactions are also not there. It's not touching a surface. It's moving in the space. So, in the first 2-3 questions, there was a weight downward and a normal reaction upward. But here you don't have to worry about them. You are in the space. So normal reactions are not there. It's not touching a body, touching a surface. And weight is also not there. It's in the space. So you don't need to worry about them. Friction of the space is also neglected. If you are going to worry, the only fact you have to consider is the forces due to the explosion. But again, always the force is created with the Newton's third law companion. As you are considering the full system here, they will cancel out. So without any hesitation, you can apply LMC to the initial direction. Initially, what are the momentum components? 50 into 100, that's all. What are the initial momentums? Mass 50, velocity 100. What are the final momentums? 25 into minus 30. Velocity is a vector. If the velocity changes the direction, it should be indicated by a minus mark. Now you are applying the equation to the front direction, but one fragment moves to the opposite direction. So you have to indicate that with the minus mark. Velocity is a vector. If it changes the direction, it should be minus in equations. So the 25 kg fragment moves to the opposite direction from the initial. So it should be a minus when you apply the LMC to the initial direction. 50 into 100, 25 into minus 30 plus 25 into V, momentum from the other fragment. 5000 is equal to minus 750 plus 25V. 5750 divided by 25 is the velocity of the other fragment. Okay. (230 meters per second). You got a plus value for the velocity V of the other fragment. You got plus 230. What do you mean by plus? It is in the initial direction that you consider. If you get a minus value for the velocity, it will hint you that the velocity is in the opposite direction, not in the direction that you consider. But here, no problem. You got a plus sign for the answer. That means the considered direction is correct. To the considered direction, to the initial direction, that fragment will have a 230 meters per second velocity. Okay. Then move to question number 12. A stationary bomb explodes into two fragments. A stationary bomb explodes into two fragments. Mass of one fragment is 3 times that of other. Let's say the complete mass is 4m. Now it's exploded into two fragments, one m and other 3m. The complete mass is 4m. It has exploded to two fragments, one m and the other 3m. If the lighter fragment moves at a 90 meters per second velocity, if the lighter fragment moves with the velocity of 90 meters per second, find the velocity of the heavier fragment. Find the velocity of the heavier fragment. Okay. Okay. Now look at the board. If it is a conservation, that means the final and initial values are same. So what is the initial momentum? What is the initial momentum here? It's 0. If it is a conservation, if it's called a conservation, that means the final and initial values are same. So initially the bomb is at rest. So the initial momentum is 0. If it conserves, the final momentum should also be 0. If so, look at the board. I know that you have done this, but look at my approach. Listen to these sayings. Now, initially, the bomb is at rest. So, it doesn't have a momentum. Why? Velocity factor is 0. So, if it is conserved, if the momentum is conserved, as there are no any external forces, there might be forces born in the collision, but each and every force born with the Newton's third law companion. As you are considering the system, they will cancel out. Listen to this. Now, there are no any external forces here. No friction, no nothing. There's a bomb at rest. There might be forces acting on these fragments at the collision, due to the collision. But each and every force bonds with the Newton's third law companion. As you are considering the full system, they will cancel out. So you can apply the LMC. No any external forces, you can apply LMC. When you go to apply LMC, linear momentum conservation, it's a conservation. The final value is equal to the initial value. Initially, the bomb is at rest. So the initial momentum is 0. So applying LMC will give you the idea that the final momentum is also 0. How this final momentum will become 0? Final momentum can become 0 if these fragments simplify their velocity, simplify their momentums by moving to opposite directions. As the bomb is at rest in the beginning, the initial momentum is 0. Due to the conservation, the final momentum should also be 0. How you can make it 0? If this fragment with the mass 3m into v, the momentum of that, if it is moving in this direction, the other fragment will move in the exact opposite direction. Mass m, velocity 90. Now what will happen? 3m into v in this direction can cancel out with m into 90. Then what will happen? Vectors will cancel out. 3m into v to this side and other part will move exactly in the opposite direction m into 90 with the momentum m into 90. From there you can find this v. V is equal to 30. So that is the case. If the initial momentum is 0, final momentum should also become 0. For that, if there are two fragments, they should separate and move in exact opposite direction, carrying the same momentum to both sides. It will make the momentum to cancel out, leaving the final momentum 0. If it is an explosion, if there are two fragments, if the bomb was initially at rest, the final momentum should also be 0. To do that, two fragments can move exactly in opposite directions with same momentum values. Then the momentums will cancel and give you a final 0 momentum. To do that, here the velocity of the higher fragment should become 30. Okay. If the initial momentum is 0, the final momentum is also 0. To do that, finally, when the object, the exploded fragments, they are moving. While they are in motion, how can the final momentum become 0? Here, this is the point. Two fragments can move in exact opposite directions with same momentums. Then these two momentums will cancel out, will give you a 0 momentum. And it is conserved by initial momentum is also 0. So the higher mass will have a velocity of 30 exactly in the opposite direction of 90. The higher mass will have a velocity of 30 exactly opposite to the direction of the lighter, exactly opposite to the velocity of the lighter mass. 90 and 30. 90 and v are in exact opposite directions. M into 90 equaling 3m into v and cancelling each other, creating a 0 momentum to the system. Okay. Question number 14. Question number 14. A stationary bomb. Initially, the bomb is at rest, 75 kg in mass, explodes into two fragments of mass 25 and 50. 25 kilograms, 50 kilograms, 25 and 50. If the 50 kg fragment moves at 5 meters per second velocity, 5 meters per second velocity in the forward direction, find the velocity of 25 kg fragment. Let's say V dash. V dash. Now you have to understand the system. It's a bomb in a stationary position. No frictions, no any other external forces. Okay? And when it explodes, there might be forces created due to the explosion, but they will cancel out each other when you are considering the complete full system. So initially, as it's at rest, initial momentum is 0. So from the conservation, the final momentum is also 0. If there's a value for the initial momentum, if it is conserved, you will have the same value for the final momentum. If there's a 0 value for the initial momentum, and if it is conserved, you will get the 0 value for the final momentum also. So the here, as it's at rest at the beginning, 0 momentum, due to the conservation, final momentum is also 0. Final momentum is also 0. Okay, how can the final momentum become 0 while the fragments are in motion? No problem. These two fragments can move exactly in opposite directions, cancelling their momentums to become the final momentum 0. 50 into 5, that fragment will move in a direction having a momentum of 50 into 5. The other fragment, lighter one, 25, will move exactly in the opposite direction, cancelling out the previous momentum. So 25 into V dash will cancel out the 50 into 5 momentum by moving these two fragments exactly in opposite directions. Okay, that will happen. Meantime, what is the value for V dash? You can simplify. 50 into 5 over 25. 10 meters per second. So for the momentum to be conserved, the lighter weight should move with a velocity of 10 meters per second, exactly in the opposite direction of the other. Okay. Question number 16. Question number 15. After the question number 14, I have asked you to solve the 16, but I need the 15 also. Okay, I need question number 15 before the 16th one. Let's do it there. Before the 16th one, I need the question number 15 also. Question number 15 before the 16th. Let's go to question number 15. Now, this is the situation. There are two masses. One, as I can remember, this is a A-level past paper, MCQ. One with the 10 kg mass and other with the 1 kg mass. There are two masses, one with 10 kg value and the other one is with 1 kg value. And these two masses are connected to each other by a spring. These two masses are connected to each other by a spring. Now, this inside this spring, there's a string connecting them. Now there are two masses, 10 kg and 1 kg. They are connected by a spring. Inside this spring, there's a string. There's a string. There's a spring and there's a string. What will happen? Then this system is at rest. So the initial momentum is 0. So initially this system is at rest. So the initial momentum is 0. Okay. So initially this system is at rest. So the initial momentum is 0. Then what will happen? You are asked to cut the string. You are asked to cut the string. Then what will happen? After you cut the string, the spring will not remain in this situation. It will expand. It will expand, and what will happen? Two masses will move in opposite directions. Two masses will move in opposite directions. 10 kg will move with the velocity. 1 kg will move with the velocity of 20 meters per second. 1 kg will move with the velocity 20 meters per second. And what will happen to 10 kg? It will move with the velocity v1. Initially, the system is at rest. Initially, the system is at rest. Okay. Then, after we cut the spring will not remain in the same situation. It will try to expand. Alright. Then what will happen? This 1 kg will move to the right direction. Meantime, 10 kg will move to the left direction. If the initial momentum is 0, final momentum should also become 0 from the conservation. For the final momentum to become 0, two objects should cancel out their momentums in opposite directions. So 1 kg will move in velocity 20 to this direction, giving a 1 into 20 momentum. It should be cancelled with the other momentum, 10 into v1. 10 into v1. 10 into v1. Okay. 1 into 20, the momentum to the right side should cancel with the momentum to the left side, 10 into v1. Then what will happen? v1 is equal to 2 meters per second. 2 meters per second. Okay. Now, I'm coming to question number 16 before the interval. After the question number 16, we will go to the interval. What about question number 16? What about question number 16? There are two boys. Initially, they stay close to each other. There are two boys. Initially, they are touching each other's hand. And, sorry, then what will happen? They will push each other, and this one is moving to this direction. I will draw it as the second picture. And other boy, he has moved to the opposite direction due to the push. Okay. How to solve this? Okay, Pute, now look at the board. Now look at the board. Two boys, A and B, are standing on the ice surface. Pute, listen to me. Now, can you say why they have mentioned the ice surface? It should be a smooth one. Why? If not, the friction is activated. Friction will be a external force, leaving that you can't, that it will create a situation where you can't apply LMC. To apply LMC, linear momentum conservation, there should be no any external forces on the considered direction. For that, they have given you it as a ice surface, so negligible friction. Okay. Now, initially, there's a comparison of weights. If the mass of A is twice the mass of B, if the mass of A is twice the mass of B, this is the child A, it's twice the mass of B, 2m, and child B is having a mass M. Okay? If the mass of A is twice the mass of B, correct? 2m and M. A moves, okay. Put now, what happens? Now, initially, they are very close to each other, touching each other's hand. As they say, they push each other. So, when they are pushing each other from here, there's a force from this person, from A on B's hand, and from Newton's third law, there will be a force acting on A from B's hand also. So, there are two forces. But what will happen? They are Newton's third law companions, they will cancel out. When these A and B children, when they are pushing each other, there will be two forces in equal and opposite directions. The force created on B by A and the force created on A by B. They are not Newton's third law companions. When you consider the complete system, they will cancel out. So it's ice surface, no friction. These two forces, when they are pushing each other, is cancelled as they are Newton's third law companion. So horizontally, LMC is valid. The masses of the weight of the child, it's vertical. Weight of the child, it's vertical. So horizontally, LMC is applicable. There's no any problem to apply LMC in the horizontal direction. No any problem to apply LMC in horizontal direction. Why? The weights are vertical. No need to worry about that. We can apply the horizontal LMC. Horizontally, there might be frictions, but it's side surface, so neglected. Horizontally, there are these two F forces, but they are also cancelled as we are considering the system. Both are cancelled to each other. Okay. So, no any problem applying LMC in the horizontal direction. Horizontally, what is the initial momentum? Initial horizontal momentum, it's 0. Initially, both of them are at rest. Initially, both of them are at rest. So, the initial horizontal momentum is 0. So, from the conservation, what is the final horizontal momentum? It should also be 0. As the initial horizontal momentum is 0, the final horizontal momentum is also 0. How can the final momentum become 0 while the objects are in the motion? Now, initial horizontal momentum is 0. So the final momentum should also become 0. But it's very clear, these two children are in motion. VA and VB are the velocities. So how can the final momentum become 0 while there are velocities present? Okay, final momentum can become 0 while there are velocities by cancelling the momentum in equal and opposite directions. Mass of B has a velocity VB in this direction. Mass of B, MB, has a velocity to the given direction, to this direction, creating a momentum MB into VB. If it cancels with the momentum of the other child, then the combination will become a 0 momentum. Mass of MA, mass of the child A, is moving with the velocity to the opposite direction, to this side. So it will create a momentum to the other side, MAVA. If these two momentums to opposite directions are equal, that means they are cancelled. So the result is 0. Initial momentum is also 0. That's what we need. Initial momentum is 0. So the final momentum should also become 0. You can do that while the velocities are present. How? One momentum, let's say the momentum on B, should cancel out with the momentum of A in the other side. Cancelling means again the final is 0. So MBVB to that direction is equal to MAVA to this direction. Okay. So MB, let's say child B has moved a distance x from the initial point. Let's say the child B has moved a distance x from the initial position. So I can say his velocity VB by x over t. Wait, I'll take the regular symbol that we use here. Not x, it's s. Let's say s. Child B has moved distance SB to this direction. So what is his velocity VB? The distance traveled SB over time t. After the separation, now after a time t, child B has moved the distance SB to this direction. So what is the method to explain his velocity VB? Distance over time, SB over t. Within the same time, child A, within the same within the same time, child A has moved distance SA to this direction. So what is the method to explain his velocity? Mass MA here, velocity, displacement over time, SA over T. In a considered time after the separation, child B has moved the distance SB. What is the method to explain his velocity? SB over T, displacement over time. Within the same time period, child A has moved to the opposite direction from a displacement SA. What is the method to explain his velocity? Displacement over time, SA over T. Now, you ask the thing simultaneously. That means, wait, I'll explain. So, you can write up to this position. Now, you can substitute the masses. Mass of A is equal to 2M. And mass of B is equal to M. And again, the distance traveled by A is equal to 4 meters here. So SA is equal to 4 over T. They ask you to find the distance traveled by B within the same time period. Within a time period T, A has moved the displacement SA 4 meters. So here the velocity is equal to 4 over T. Displacement is 4 here. So you have to find the other displacement SB. SB over T is present now. What will happen? T will cancel out. M and 2M. Factor M will be cancelled out. 2 into 4, 8 is equal to SB. When A travels the distance 4 meters value to the left side, B has moved 8 meters to the right side. B has moved 8 meters to the right side. This was also a exam MCQ. This was also a A-level exam MCQ. Okay. Initially, they are at rest, so the initial momentum is 0. So to be conserved, the final momentum should also become 0. For the if the final momentum is 0, while the velocities are present, the momentum should be in opposite directions, cancelling each other. So MBVB in a certain direction should cancel with the MAVA in the other direction. And there, the velocity can be explained by as they are constant velocities. As these are constant velocities, velocities will not change. Why? You are in a smooth surface. Velocities will not change. Why? You are in a smooth surface. No friction to deduct the velocity. No friction to decrease the velocity. So velocities will remain constant. So you can write the velocity by displacement over time. They ask to find you the properties of the other person after a same time period, same t. So you can write the other velocity by the displacement over same time. Okay, so you can substitute these things and time is cancelled because you are considering same time period, and you can get the answer for displacement of B. Okay, after the interval, you have to follow this. After question number 19, I need you to solve question number 21. After question number 19, you have to solve question number 21. Okay, we'll meet again around 10:35. Now what's the time? It's 10:15. So let's meet around 10:30. Okay, now we have done up to question number 15. Now you have to move for question number 6. Yeah, we did up to 16. We did up to 16. Then the 17th question. Question number 17 will be the first part to discuss after the interval. Question number 17. Question number 17. Okay. A man of mass 80 kg, question number 17. A man of 80 kilograms is keeping a zero point 0.2 kg ice ball in his hand. 0.2 kg ice ball in his hand. Stone on his hand. And as the next step, he throws this 0.2 kg ball or the stone horizontally with a velocity of 30 meters per second. Actually, this thing will not move horizontally from there onwards. It will become a projectile motion. It's true, but for the certain instant, it's thrown horizontally. Okay, there's a 80 kg man with a stone 0.2 kg in mass. They are at rest. Okay, so the initial momentum is zero. Initial momentum is zero. They are at rest. Okay. Then what happens? Then this man throws the ball to the front direction horizontally. With time, this ball will become a projectile motion as it can't move horizontally due to the gravity. But at the certain instant that we are considering, it was thrown horizontally with the 30 meters per second velocity. Okay. So I think they have neglected the friction from the ground. I think they have neglected the friction from the ground. If the friction is there, the man will not move in the opposite direction. Due to the friction, he will stop at the same place. But here, I think they have neglected the friction. So when the ball is thrown in the rightward direction, to be momentum to be conserved, the man's body will move in the opposite direction. Let's say if this is ice surface, then you can see this. If it's a surface with the normal friction, you can't see this. Due to the friction, conservation of momentum will be not there. But let's assume that this man is on an ice surface, so the friction from the ground is not available now. So the momentum conservation is valid. So to conserve the momentum, the 80 kg man will gain a velocity to the opposite direction. Let's say V. Initially, the system is at rest, so the initial momentum is zero. So the final momentum should also become zero. For the final momentum to become zero, the momentums related to each object should cancel out each other. 0.2 into 30, 0.2 into 30 should cancel out with 8 into V. 8 into V. 0.2 into 30 should cancel out with 8 into Vm. So Vm is equal to 0.2 30 80. 0.2 30 80. What will happen? 0.6 over 8. 0.75 meters per second. Okay. 0.075, no? 0.075. Okay. Now move to question number 17. Sorry, 18. Uta, in question number 18, fourth part, you have to give up the fourth part. Question number 18, fourth part, you have to give up it. You can come to that part. I will add the same question again when we are in the impulse section. After the conservation of momentum. Tomorrow, not tomorrow, next week, we have to do this impulse. That's another small lesson called impulse, Avegya. So the question number 18, part number 4, it is from impulse. So you have to leave it. So I have given this question as it was a past paper question. I gave it to you. And in that past paper question, the fourth part is related to the impulse. We will solve it next week after we learn that part. Okay, you can do the first 3 parts now. Question number 18, first 3 parts. Question number 18, first 3 parts. An airplane of mass 8,000 kilograms. That's an airplane having a mass of 8,000 kilograms moving horizontally at 300 meters per second velocity. Moving horizontally at 300 meters per second velocity at a height of 720 meters from ground. At a height of 720 meters from ground. Okay. This plane explodes into 2 equal fragments due to an initial internal explosion. This plane explodes into 2 fragments due to internal explosion. ඔයගොල්ලෝ දන්නවද ෆයිටර් ජෙට්ස් වල පයිලට් තියෙනවනේ ඉජෙක්ට් වෙන්න ඔප්ෂන් එක. හැබැයි කිසිම පැසෙන්ජර් ප්ලේන් එකක ඒ ඔප්ෂන් එක නැහැ. පයිලට් ඉජෙක්ට් වෙන්න බෑ පොත්තමක් නැහැ. එයාත් නැරෙන්න ඕනේ සෙනගත් එක්ක. සහ එයාලගේ පොඩි එතික් එකක් තියෙනවා. ඒක පයිලට්ලා කරනවා හරිද? සාමාන්‍යයෙන් එයාලා කොලිෂන් එකක නම් ඉන්නේ. එයාලා ඒක සිරාවට ඒගොල්ලෝ කරනවා හරිද? එයාලා වාහනේ ප්ලේන් එකේ නෝස් එක හරව ගන්නවා ඉස්සරහට. එයා තමයි ඉස්සෙල්ලා පොළවේ වදින්නේ. පැසෙන්ජර් එක්කෙනෙක් හරි බේරෙන්න කියලා හිතාගෙන එයා ඇන්ගල් එක පුළුවන් නම් ඒ කියන්නේ ඒ වෙනකොටත් ඒක මූවබල් නම් ප්ලේන් එක කඩන් වැටෙන අතරේ පොඩ්ඩක් හරි මූවබල් නම් එයා හදා ගන්නවා ප්ලේන් එකේ නෝස් එක බිම වදින්න. හරි එතකොට පිටිපස්සේ නැට්ටේ ඉන්න පැසෙන්ජර් කෙනෙක් හරි බේරෙන්නේ. හරි එහෙම කරපු පයිලට්ලා ඉන්නවා ලෝකේ ඕන තරම් සහ එහෙම කරනවා මිනිස්සු හරි. පයිලට් කෙනෙක් කියන්නේ තම වීරයෝ ඉතින් හරි එතකොට එක පැසෙන්ජර් කෙනෙක් හරි බේරෙන්න කියලා හිතාගෙන එයා තමයි ඉස්සෙල්ලා පොළවේ වදින්නේ මෙහෙම කොලිෂන් එකේ. පුළුවන් නම් ඒ කියන්නේ මැනුවරබල් නම් නෝස් එක පහළට අරන් එන්නේ හැප්පෙන්නේ. හරි. එතකොට an airplane of mass 8,000 kilograms moving horizontally at 300 meters per second velocity at a height of 720 meters and it explodes into 2 equal fragments due to internal explosion. Okay, let's draw the next part. Now the plane has exploded into 2 parts. First one and the nose part. And one fragment moves at 800 meters per second velocity to initial direction. So the nose has gained a velocity of 800 meters per second to the initial direction. Find the velocity of the other fragment. Find the velocity of the other fragment. Now the plane was moving horizontally, so the vertical forces, mass, those things will not affect. We'll neglect the air resistance also. So horizontally, LMC is applicable. Horizontal, the weight is vertical. So horizontally, LMC is applicable. Applying LMC horizontally to the plane. Applying LMC horizontally to the plane. Okay, when we apply LMC horizontally to plane, what are the initial momentums? 8,000 into 300. Initial momentum is 8,000 mass into 300 velocity when the complete plane is present. And in the collision, there will be forces created on each other, on each part, but they will cancel out. They will cancel out. Okay. So, what will happen? No need to worry about external forces, and the motion is also horizontal. No worries about the weight, it's vertical. So, applying LMC, 8,000 into 300 is the initial momentum. What are the final momentums? One part, they were equal parts which were exploded. One part had a mass of 4,000 and got a velocity of 800. And the other part, as they are equal parts, it's also having a mass of 4,000 and a velocity of V1. And a velocity of V1. Okay, so this is the situation. I will simplify it. I will simplify it. 24 is equal to 2,400 is equal to 2,400 is equal to 3,200 plus 4V1. Okay. Now 2,400 minus 3,200 is equal to 4V1. So minus 800 is equal to 4V1. Minus 800 is equal to 4V1. V1 is equal to minus 200. V1 is equal to minus 200. So the V1 is equal to minus 200. Okay, what do you mean by minus 200? If the velocity vector comes with the minus value for answer, it means the opposite direction. If the velocity vector comes to us with the minus mark as the final answer, it hints us the opposite direction. So what has happened? After the explosion, the first part has moved in the same direction with the velocity of 800, while the other part has moved in the opposite direction with the velocity of 200. That's the meaning of minus 200. Okay, now it's clear. Nose part, it moves with the velocity of 800 to the initial direction of the plane, while the tail, after the explosion, it moves with the 200 meters per second velocity to the opposite direction with respect to the initial. Okay. The velocity of the other fragment, it's minus 200. First question. The second subpart, time taken for each fragment to reach the ground. Okay. At the collision, they will move apart horizontally. At the collision, they will move apart horizontally, but after that, they are in the Earth's gravitational field. So, meantime, they are having their horizontal motion, they will come down to. It will end up with a projectile motion. You can't neglect that fact. At the moment that they collide, that they explode, they will move apart with horizontal velocities. Yes, that's true. But after that, what will happen? They will move in a projectile motion. Why? Meantime, the horizontal velocity is there. There's the acceleration of gravity downward for the exploded fragments. So they have to face that. So they will come down while they are moving horizontally. So moving horizontally and coming down together. What happens? They will be in a projectile motion after that. So this projectile is a projectile which initiated from a level 720 meters from ground. So to reach the ground vertically, it has to move 720 meters downward. Okay. Applying S equals ut plus half at square. Applying S equals ut plus half at square downward. It has to move downward with a meter value of, it has to move 720 meters downward to reach the ground. This thing happened at a 720 meter height. Initially, the fragments move apart with horizontal velocities. So their initial vertical velocities are 0. When applying S equals UTA plus half at square downward, the initial velocities are 0. 720, initial velocity is 0, half under the acceleration of gravity t, 10 t square. Okay, what will happen? 144 is equal to t square, t will be 12 seconds. Time will be 12 seconds for one fragment to reach ground. It will take 12 seconds for a fragment to reach ground. They will move apart horizontally, fulfilling the conservation of momentum. But after that, they are in the free space. So they have to face the motion under gravity. So acceleration of gravity is plus 10 downwards, and they will take 12 seconds to pass the 720 meter downward and hit the ground. In the other side also, you can do the same thing. No need to write it again. S equals ut plus half at square. You don't need to repeat it. Why? When we consider the vertical motion, both are same. Why? Other fragment is also having a 0 initial velocity vertically. Other fragment moves apart to the opposite direction in the horizontal. So it also have a 0 velocity downward. 0t plus half acceleration of gravity 10 t square. It also has to reach a 720 meter downward length. Okay, what will happen? 144 is equal to t square. T is equal to 12 seconds. T is equal to 12 seconds. Okay. Okay, it will take 12 seconds to reach the ground. The third one, the horizontal distance traveled. Within this 12 seconds time, both of them will have their own horizontal ranges. Why? I'll apply S equals UT to this one. After the collision, to conserve the moment, after the explosion, to conserve the momentum, this got a velocity of 800 to the horizontal. Until it reaches the ground, it takes 12 seconds. Within this 12 seconds time, this 800 velocity horizontally will give the horizontal range, 800 into 12. 9,600 meters horizontal range for the nose. What will happen to tail? Applying S equals UT to the other side. Velocity is 200. Time is equal to 12 to reach the ground. Within that time period, 200 horizontal velocity will create the horizontal range to the left side. 2,400 meters. 2,400 meters. These are the horizontal ranges they go to. And question number 4, the average force acting during the explosion. The average force acting during the explosion. I will do that part with a question, not with a single question, with a question from the impulse lesson. If you have done impulse in your class, sorry, in school, if you have done impulse your school, how to solve the fourth part? Ft equals mv minus mu. Ft equals mv minus mu. Okay, you are applying Ft equals mv minus mu to this nose. The force acting on the nose is F. Force acting on the nose is F. You are applying Ft equals mv minus mu to the nose. Force acting on the nose is F. Time is 0.4 seconds. What happened? Mass 4,000 into velocity 800. Initially, nose had a velocity of 300 minus 4,000 into 300. This is the way to get the answer. I'm not going to discuss this as I'm doing it next week. I'm not going to discuss the fourth part. ඉස්කෝලේ හදලා තියෙනවා නම් පුතාට බලා ගන්න නිකන් හැදුවේ. මේක මම next week කරන කැලලා. Okay. Applied Ft equals me minus mu to the nose. The force acting separately on nose is F for 0.4 seconds. What happened to the nose? mv 4,000 into 800 minus m 4,000 into 300 and it was initially. Wait, I'm not going to explain it. Okay. I'm coming to question number 19 then. I'm coming to question number 19. Question number 19. Question number 19. A cannon, a කාලතුවක්කුවක් of mass 50,000 kilograms fires the 8 kg shell horizontally at 200 meters per second velocity. Find the recoil velocity of the cannon. Okay. If you have finished up to question number 19, then it's 21. Then these are the other questions. Question number 22, 24. Question number 22, then question number 24. Then 25, 27. Okay. Let's reach to that level. I'm in the question number 19. I'm in the question number 19. In question number 19, they mentioned a cannon. කාලතුවක්කුවක්. It has a mass of 50,000 kilograms. And from this cannon, a shell is fired with a mass of 8 kg. කාලතුවක්කුවෙත් බරයිනේ. It's 8 kg. At a velocity of 200 meters per second. Velocity of 200 meters per second. Find the recoil velocity of the cannon. Find the recoil velocity of the cannon. Okay. What do you mean by recoil velocity? පුතා චුට්ටක් වැඩ නවත්තමු. පොඩ්ඩක් මෙතන physical situation එක කතා කරලිමු. අපි පොඩි කාලේ ඉස්සර ගියා ඇමරිකා funniest home videos කියලා වැඩසටහනක් තිරසෙටපු විදිහ. අයමත් කියනවාද මන්ද? ඇමරිකාස් funniest home videos කියලා. ඒකේ මට අද වගේ මතක සිද්ධියක් තියෙනවා. ඒකේ අර මේ ෆයර් කරලා නැති අයට තුවක්කුවක් දෙනවා ෆයර් කරන්න. හරි ෆයර් කරලා නැති අයට තුවක්කුවක් දෙනවා ෆයර් කරන්න කියලා. ඒ රටේ තුවක්කු තියෙනවනේ. හරි ඉස්සරහට ෆයර් කරද්දි මේගොල්ලෝ හුරු නෑනේ. පස්සට ගිහිල්ලා වැටෙනවා. ඉතින් අනික් අය බක බක කාලා hina වෙනවා. hina වෙන එක හරි නැහැ. hina වෙන එක හරිම වැරදි. ඒක අනුමත කරන්නේ නැහැ. මිනිස්සුන්ට සලදරයක් වෙන එකට hina වෙන එක. නමුත් ඉතින් ඒක තමයි මේ වීඩියෝ එක ගැන මම මේ කියන්නේ. හරි ඉස්සරහට ෆයර් කරද්දි මේ මිනිස්සයා පිටින්ම පස්සට ගිහිල්ලා වැටෙනවා පුරුදු නැත්තම්. ඇයි ඒ? ඒක පොඩ්ඩක් කතා කරමු. කාලතුවක්කුවකත් ඕක අපි දැකලා තියෙනවා. ඔය නිදහස් උත්සවයට එහෙම කාලතුවක්කුව වලින් මුහුදට වෙඩි තියද්දි කාලතුවක්කුව මොකද වෙන්නේ ජොක් ගාලා? පස්සට යනවා. ගිහිල්ලා ඉන්නේ. ඒ මොකද්ද වෙන්නේ? ඒ මොකද්ද වෙන්නේ? මෙයාලගේ දැන් ෆයර් කරන්න කලින් initial momentum එක 0. මේගොල්ලෝ rest එකේ ඉන්නේ. So the gun and the shell both of them are at rest. The complete system is at rest in the beginning. So the initial momentum is 0. If the initial momentum is 0, what should happen? As there are no any external forces in the horizontal direction, the final momentum should also become 0. How the final momentum can become 0? When the bullet is fired, when the shell is fired, it will take a momentum to the front side, mass 8 into velocity 200. So the momentum gained by the bullet 8 into 200 should be cancelled with the momentum gained by the cannon to the opposite direction. Its weight mass is 50,000 and the recoiling velocity is v1. This phenomenon is known as the recoil process. This phenomenon is known as the recoil process. මෙන්න මේකට සිංහලෙන් කියන වචනේ ඊටත් හපක්. වාංගු වීම. තුවක්කුවකින් ඉස්සරහට වෙඩි තිබ්බහම තුවක්කුව පස්සට විසික් වෙන එකට සිංහල වචනේ වාංගු වීම. ඒක ඊට හපක්. ඉංග්‍රීසි වචනේ recoil. හරි? එතකොට මොකද්ද වෙන්නේ? The cannon will recoil to the backward direction while the shell is moving to the forward direction. Forward momentum 8 into 200 is equal to 50,000 into v1 to the other side. So you can find the recoil velocity 8 into 200 divided by 50,000. Okay. 16 into 500. 32 over 1000. 0.032 meters per second. 0.032 meters per second. Okay. Then question number 21. Question number 21. Question number 21. A 58 kg athlete runs. So, there's the athlete with a mass of 58 kilograms. What happens? He runs at a velocity of 6 meters per second. Velocity of 6 meters per second and jumps into a stationary trolley of mass 2 kg. And there's a stationary trolley with a mass of 2 kg. Then what happens? He jumps into the trolley. Now he is on the trolley. Now we are in the horizontal direction. They haven't mentioned the frictional forces on the surface, so I'm neglecting them. Weights and the normal reactions upward, they are vertical, they will not affect the horizontal. And when the athlete jumps to pulley, there will be forces on him upward. Meantime, there will be forces on the trolley downward at that collision. But each and every force born with the normal reaction, born with the third law companion, when you consider the system, they will cancel out. So without any problem, I am applying LMC to the rightward direction in the horizontal. Linear momentum conservation, horizontally rightwards. Arrow and LMC trace. I have to write it in the exam. Okay. So what are the initial momentums? 58 into 6. Momentum component of the man at the beginning. 58 into 6. Plus 2 into 0. Initially the trolley is having a 0 velocity. It is at rest. So 2 into 0. These are the initial momentum components. They are equal to the final momentum. Finally, the trolley and the man moves as a one. Man moves on the trolley. So they can be considered as a single object. So the mass is equal to 58 plus 2. That single object, trolley and the man, will move with the velocity of V dash. What will be that V dash? Let's say it's V with the velocity of V. Okay. 58 into 6. 60 into V. 58 into 6 over 60 is the velocity. 5.8 meters per second. Velocity is equal to 5.8 meters per second. Velocity is equal to 5.8 meters per second. So after he jumps to the trolley, both of them will start to move forward with the 5.8 meters per second velocity. That's the first thing. Then what will happen? It's the Roman number 1 in part A. Roman number 2 in part A. What they ask, find the velocity of the system after the collision of the second athlete. Now there's another problem. Now I will continue the diagram, or you can go to a separate one. Now this 58 kg man on the 2 kg pulley is moving to the front direction with the 5.8 meters per second velocity. Meantime, he meets the second athlete. There's another athlete. He's not on a pulley. He's just running on the ground to the opposite to meet this one. His weight mass is 90 kilograms. And he's having a velocity of 17.2 meters per second. And he's in a head-on collision with the first athlete and the trolley. So I have continued the diagram. You can draw a new one. No, you also can continue. Now this 58 kg person with 2 kg trolley, he's moving to the rightward direction with a velocity of 5.8 meters per second. Meantime, the second athlete who had a 90 kg mass, he's on a head-on collision with this first car with a 17.2 meters per second velocity. Okay. What will happen? These two people will meet each other and you will get a combined picture like this. Now the trolley is there. On the trolley, now there are two athletes. On the trolley, now there's another athlete present. He has also jumped into it. And what will happen to the trolley. After that, we'll say the combined velocity is v dash. Okay, again applying LMC. Applying LMC again to the front direction horizontally. Applying LMC again to the front direction horizontally. Okay. This 58 kg man with a 2 kg trolley will end up with a 60 kg mass having a velocity of 5.8. So the momentum of that part, 58 plus 2, 60 kilograms into velocity of the man and the trolley, 5.8 to the front direction. It's the initial momentum plus there's another momentum component 90 into minus 17.2. There are two momentum components at the beginning. Now this man with the trolley, the man who is on the trolley, they are moving to the front direction with the 5.8 velocity. So the total mass 60 into 5.8 is the momentum component from there. Meantime, there's another man coming on a head-on collision. Mass 90, velocity 17.2. Now he is coming to hit the initial one. So it's in the opposite direction. So the velocity should be minus 17.2 plus into 90. These are the initial velocity momentum components. And this man also jumps to the trolley. Now, both of them will become the new combination. So what is the mass of this new combination? 60 plus 90. 58 plus 2 was the mass from the earlier case. And now the second man also has jumped to the trolley. So 60 plus 90 will be the total mass. That mass will gain the velocity of v dash horizontally to conserve the momentum. Okay. 60 into 5.8 plus 90 into minus 17.2 is equal to 150 into new velocity of the system after both men are on the trolley. $60 into 5.8, 348. 90 into 17.2. Minus beta minus 1548 is equal to 150 into v dash plus 348 minus 1548 will end up with the minus 1200 value 150 v dash. V dash is equal to minus 8. So I got a minus mark again, no worries. That means after the second man jumps to trolley, trolley has changed its direction. Now the complete system is moving in a backward manner with a minus 8 velocity. Now the complete system again moving to the backward direction with 8 meters per second velocity. So that is the meaning of that minus mark. There was a man, he ran forward and jumped to a trolley. From the momentum conservation, man and the trolley got a velocity of 5.8 and they were continuing. Meantime, there was another man running toward the first man and he also jumped to the trolley again. After that, to conserve the momentum, the complete direction of the trolley was also changed. And front direction LMC gave you a minus 8 final velocity. That means now both men on the trolley are moving backward with the 8 meters per second velocity. Okay, so find the velocity of the system after the collision with the second athlete. It's 8 meters per second, but minus. That means to the opposite direction. Now they both of them are coming back. And when they are coming back, they will fell into a hole. That's what the next part is. Okay, I have to go to a separate diagram. Okay, now I'm coming to the part B. Now I'm coming to part B. Now it's very well understood that after the second man jumps to the trolley, trolley will completely alternate its direction. And now both of them are on the trolley. Meantime, both of them are on the trolley. And due to the previous situations, now the trolley has a leftward velocity of 8 meters per second. Now, after the second conservation of momentum theory or the law, now we gain the final answer. Now both of the men are on the trolley with the 8 meters per second velocity to the left side. Here, a new situation occurs. If the system now moves along through a surface of length 2.5 meters, now on that direction, after 2.5 meter length, there will be a, they will fall down from a height of 45 meters. You don't have far to that direction. They will fall down into a lower state, lower ground. Okay. Now, if the system now moves along with a rough surface of length 2.5 meters with coefficient of frictional coefficient is 0.3. Now, after the second person jumps to the trolley, now the compound velocity of the system is 8 meters per second to the left side. And as they say, to the left direction, now the trolley has to pass a rough surface with a frictional coefficient of 0.3 as the value. And then it will come to the edge. After that, this trolley and these two men will come to the edge of that certain surface, and with the velocity they have, with the horizontal velocity they have, they will enter the free space. But the acceleration of gravity is downward, so they will come in a projectile motion to hit the ground. They will come in a projectile motion to hit the ground. So this is the final situation. After the second man jumps the trolley, they have obtained 8 meters per second leftward velocity. With that leftward velocity, a 2.5 meter length is remaining before they has to jump to this lower ground level. There, meantime, they has to pass this final 2.5 meters with in a rough surface having a frictional coefficient of 0.3. Now, when they are moving in this leftward direction, what will be the frictional force acting on them to the right side, to rightward direction, as they were moving with the velocity of 8 meters per second to the left direction, the frictional force acting on them will be on the right direction, to the right hand side. What will be the frictional force value? Friction is equal to mu r. Friction is equal to mu r. Mu is equal to 0.3. What is r? The compound weight, it's 150 newtons. The trolley, it has a weight of 2 kg. And then the first man, he's having a weight of 52. He's having a mass of 52. So altogether there are 60 kilograms. And the next person, he is 90 kilograms. So altogether the weight is, the mass is 150. So the weight is 1500 newtons. They are in a horizontal motion. So the normal reaction should cancel this 1500. So the combined normal reaction is 1500 newtons upward. So the combined normal reaction, 1500 newtons upward. Now they are in a horizontal motion, no any vertical motion. Vertically downward, they are combined weight, 1500. So the R is also 1500 to cancel out. Why? They are in a horizontal motion. Vertical forces should cancel out. The total weight should cancel out with R. Friction is equal to mu R, 0.3 into 1500. 150 into 3. The frictional force is 450 newtons. Due to this 450 newtons, velocity to the left side will reduce. Velocity to the left side will reduce. He will come to the edge, let's say with the velocity v dash. He will come to the edge with the velocity v dash. Apply v square is equal to u square plus 2as to left side from the point that they start to move left side. At the edge, this system will have a velocity of v dash square. Initially, at the considering point, they got a velocity of 8 due to the conservation of momentum. 8 square plus 2 a s. They have to move 2.5 meters before coming to the edge. So we need to find the acceleration to the left side. Applied F equals ma. Applied F equals ma to the left side. Vertical forces are neglected. I am on the horizontal. When the trolley moves to the left side, there's a frictional force to the other side. So the F is minus Fg here. When trolley moves to the front left side, the friction is in the opposite and it's the only force horizontally. So applied F equals ma horizontally from the left direction. The remaining force is the only friction, so minus Fg. 150 is the combined mass A. Minus 450 is equal to 150A. So the acceleration is minus 3. Okay, I'm going to explain the 21st question again. Meantime, if you have finished, you can go to the 22nd one. You can go to the 22nd one. I'll explain the 21st question B part again. Okay, let's come to the 21st question again. In the 21st question, there was a 58-kilogram person running in the normal ground to the rightward direction horizontally. And suddenly he jumps to a trolley. And he himself and the trolley, being a combined object, moves to the rightward direction. Applied LMC there and find their combined velocity. And that was the part A, subpart 1. Then when this man is and the trolley is moving rightward in that new velocity, there was another 90 kg man coming towards him for a head-on collision with a 17.2 meters per second velocity. And again applied LMC for that system and found after the second man jumps to the trolley will have a -8 velocity from the conservation of momentum. That means both of the men on the trolley will start to come to the leftward direction after the second man jumps to the trolley. Okay, now part B starts from there. Now both men are on the trolley with the 8 meters per second leftward velocity and their combined mass is 150 kilograms. As the question says, after this second LMC, after the both men on the trolley got a velocity of 8 meters per second to the leftward direction, they have to move through a rough surface will create a friction opposite to the initial direction. Friction is calculated by mu r in a situation like this. Mu 0.3, what is r? R is the normal reaction on the object. The object is moving horizontally, so there are no resulting vertical forces. As the total weight is 1,500, upward should also become 1,500, cancelling the vertical forces, leaving the object a horizontal motion. So R will also become 1,500, where mu R becomes 450. So after these two men on the trolley enter the rough surface with the 8 meters per second velocity, friction on them is 450 to the other side. There are no other horizontal forces. This trolley doesn't have an engine to create the additional force, or there's nothing like that, just the friction to the opposite direction. So this frictional force will reduce this 8 meters per second velocity with time. Applied F equals ma for the leftward direction. Only force remaining is the rightward force of friction. So it should be when applying F equals ma leftward, this F should be the -450 value as the friction is in the opposite. So -450 is equal to 158 due to the frictional force. So the acceleration gained to the left side is -3. Yes, if the frictional force is present, the velocity will reduce with the minus acceleration. Okay, so we know the system has a 8 meters per second velocity when it starts to enter the rough area. Meantime, the acceleration, the deceleration that this system feels is equal to a -3 value. So applied V equals U square plus 2as to the leftward direction now. At the edge, the remaining velocity will be V dash. At the beginning of the rough surface, due to the earlier momentum conservation, it was 8. 2, acceleration minus 3 due to the frictional force. Yes, 2.5 meters is left before reaching the edge. Okay, by solving it, got the answer that the system, the two men and the trolley, comes to the edge with a velocity of 7 meters per second. At that moment, the horizontal will be remain same. After that moment, due to the object entering the free space, there are no any accelerations in the free space, no frictions either. It's in the free space now. So the velocity of 7 meters per second value will remain same. But in the free space, due to the acceleration of gravity, it will come down for 45 meters before hitting the ground. Apply S equals ut plus half at square downward, 45 meters. Initially, the velocity is horizontal. We can complete the conservation of momentum next week within 1 hour or 1.5 hour time. Then there's a small part called impulse. We can also finish that. And sometimes we'll be able to reach the next lesson, torque, center of gravity, and equilibrium. I have already given you the first 2 pages that you have to paste on your book related to torque. Bring it to class next week. Okay, question number 22. Question number 22. A projectile is fired at 400 meters per second velocity. A projectile is fired at 400 meters per second velocity, making an angle of 60. Making an angle of 60 with the horizontal. At the highest point of its trajectory, it will move in a parabola like this. It will move in a parabola like this. At the highest point of its trajectory, at the h max value, when it passes the h max, it faces an explosion, and it explodes into two equal fragments, m. Initially, it's 2m. One fragment falls vertically downwards. Okay, one fragment directly fall down. That's how they say. Fall down, no? Fall down. That means what has happened to this fragment? Due to the conservation of momentum, this has gained zero velocity. After the collision, this has come to a zero velocity value. So it can't stop there with a zero velocity. Then it has fallen down. That's what has happened. And what about the other one? Find the horizontal distance from the firing point to where the other fragment lands. Okay. Now at the highest point, it has exploded into two sub-fragments. And what has happened to this fragment? It falls down. To fall down, it should not have a horizontal velocity gained by the LMC. So this has reached instantaneous rest after the collision. this part has gained a instantaneous rest after the explosion. That's why it fell down directly. It can't wait there in the space. It has gained instantaneous rest after the collision, after the explosion. So it can't wait there. It has fallen down. That's what they mean. Okay. Now, I'm going to apply linear momentum conservation for this explosion. Before that, I need to find the initial velocity of the object before it explodes in the highest position. Before the object explodes into two parts, at the highest position, it's having its horizontal velocity component as its velocity. At the highest point, there's no any vertical velocity. Only remaining velocity is 400 cos 60. 400 cos 60. 200 meters per second. So, applying linear momentum conservation before and after the explosion, applying linear momentum conservation before and after the explosion. Just before the explosion, applying LMC just before and after. Just before and just after the explosion. Just before the explosion, mass was 2m. Velocity was 400 cos 60. Why? The horizontal velocity will not change. At the beginning, horizontal velocity is 400 cos 60. It won't change as this is a projectile. So, mass 2m into 400 cos 60 is the momentum just before the explosion as it is in the highest point. But what will happen after the explosion? It will be divided into two parts. One part M will come to instantaneous rest. That's why it fell down from there. If it gained a velocity due to LMC, it should have a projectile motion initiating with that horizontal new velocity. But nothing like that, it just fell down due to the gravity. Why? It was instantaneously rest after the explosion. So, when applying momentum conservation for that part, m into 0 is the momentum component on that part. The other part is also having a mass m and it will gain a velocity v. It will gain a velocity v after the explosion. 2m 400 into half mv. M will cancel out. Thousand 600 meters per second will be the velocity of the exploded other part, velocity of the other fragment. Velocity of the other fragment. Okay. It also having a downward velocity 0 at the beginning. It was moved horizontally due to LMC here. So it's not having a vertical downward velocity. So it has to reach this Hmax value downward before hitting the ground. Okay. Now I need to find the highest, this Hmax value to locate this exact position where this explosion happened. So for the projectile motion, applying v square is equal to u square plus 2a for the projectile motion. When I'm considering the first half from the projectile motion at the highest point, upward velocity is 0. Initial upward velocity is 400 sine 60. 400 sine 60 square. 2. Acceleration of gravity is minus 10 h max. 20 h max. 400 sine 60 root 3 over 2 square. 20 h max. 20 h max. 200 root 3 square. H max is equal to 6,000 meters. It was at a 6,000 meter height when this explosion happened. Okay. So the remaining part has to come 600 meters vertically down to hit the ground, applying S equals ut plus half a t square for this part to reach 600 meters downward, initially from 0 velocity, 10 t square. T square will be equal to 1200. T is equal to root 1200. Within that time, it will get a horizontal range. Applied S equals ut horizontally. After the linear momentum conservation, that fragment got a velocity of 1600 to the rightward direction. That velocity will remain for root 1200 time until it reaches the ground, creating the horizontal range R dash. Okay, so this is the answer. So this is the answer. Okay, I'll explain that question again. I'm going to finish the class and I have to go for these other questions next week. 1600 multiplied by root 1200. 55,425 meters. Wait, we'll check the answer again. Okay, first time solving it. I'm going through it again. Now, this projectile had a velocity of 400 meters per second at the beginning, at an angle of 60 where it was projected. So this is the path of the projectile. Even though this is the path of the projectile for the first half, later this path will change. Okay, I'll add the right color combination. I'll use the blue color and black color correctly for the image. This is the initial object moving in this parabolic path. It comes to this place. I'm correcting the colors. Now it's here. What is the height that it will reach? This is the object with a velocity of 400 meters per second at an angle of 60. I'm correcting the colors. What will be the maximum height that it will reach? Applying v square equal to u square plus 2a upward at the maximum height, upward velocity is 0. Initial velocity is 400 sine 60 upward. Plus 2 minus 10 h max. 20 h max is equal to 400 sine 60 root 3 over 2 square. 20 h max, 200 3 square 3, 200 square. Okay. (6,000 meters). So the h max is equal to 6,000 meters. At this point, what happens? This explodes into two equal fragments. So at this point, I applied linear momentum conservation to the forward direction. Before the explosion, the complete mass was, 2m. And what was the velocity of this 2m part? At the highest point, it doesn't have a vertical velocity, but still, as a projectile, the horizontal velocity component is remaining. At the beginning, horizontal velocity component is 400 cos 60. That means 200. It won't change throughout the projectile. So here also, there's a velocity component of 200 meters per second is remaining for the whole body. Vertical one is 0 at the highest point, but horizontally, 400 cos 60. Velocity is remaining. So when applying LMC, just before the collision, mass is 2m, velocity is 200 meters per second. Mass is 2m, velocity is 200 meters per second. Okay. Then what happens? Mass is 2m, velocity is 200 meters per second. Then what happened? After the collision, after the explosion, one part just fell down. What do you mean by that? If it gained the horizontal velocity from the explosion, it should be in a projectile path. Why it fell down? Instantaneously, it became to a zero velocity soon after the explosion. That's why it fell down after that. So that part, mass m with zero velocity, and the other part gained velocity of v, mv. These are the momentum components after the explosion. 2m into here, 2m into 200, m into v. M will cancel out. So v is equal to 400. Now that's the place I have done the mistake. Okay. So the velocity gained by the remaining fragment is equal to 400 meters per second. Now I am coming to the black color. Initial half was in the blue color. If the initial half is in the blue color, this is the imagined path for the projectile. But now it will change. I am correcting the image also. Now it will change. Why? This is the initial assumption that this projectile has to move. But due to the collision here, what happens? Suddenly, velocity has increased. At the highest point, as a combined object, it only had this horizontal component 200. It's from the blue color. But due to the momentum conservation, after the explosion, one part fell down and the other part gained the velocity of 400. So 400 is larger than 200. So what will happen? Instead of this earlier path, it will be a new parabola like this. I had to draw it from the black color. It's a new parabola like this. In this new parabola, in this new projectile motion, it has to reach this 600 meter downward. Applying S equals ut plus half at each downward. At the highest point, it was from a 6,000 meter higher level from ground. It has reached the 6,000 downward. Initially, this fragment was given the velocity of gained the velocity of a 400 meter value horizontally. So the downward velocity is 0 plus 10 t square. So the t is equal to root 1200. T is equal to root 1200. Within this 1000 to root 1200 time, due to the newly gained velocity of 400, it will have a new horizontal range like this. It should be in black color, R dash, the new horizontal range from here. Why? At the highest point, before the explosion, it had the velocity of 200 meters per second. Due to the conservation of momentum, as one falls down there, the other got a velocity of 400. So it's a higher velocity than the initial one at the highest point. So it will create a new parabolic path like this. And this is the new horizontal range. Okay, it will take root 1200 seconds to reach this 6,000 meter height downward. Within that time, it will get a new horizontal range like this. applying S equals ut, velocity is 400. Velocity is 400. That's the point where I did the mistake. And time is root 1200. Okay. 400 multiplied by root 1200. 13,856. 13,856 is the length from here to here. But they ask you the horizontal range from here. So you have to use the initial parabola to find this part, R0. And add that part to this new answer, then you will get this exam answer. Okay? They ask you to find the position where the second fragment lands with respect to the initial point. So from here, it's a new parabola and you have to calculate R dash. Meantime, you have to add this R0 from this side. Then you will get the final answer. Okay? Then you will get the final answer. හරිද එහෙනම්? නා. හදලා දෙන්නේ ඉවරද? හරිද? නා. Okay. හරි මේ 12යි 5යි වෙලා. Okay, next week, this is the plan. I'm going to start from the 24th question. I had to mark them. No? Next week, I'm going to start from the 24th question. Question number 24, then 25 and 27. And I have to continue up until the 34th question. Okay. Okay, so let's finish the class. And 400 cos 400 and sin 60. Due to this 400 and sin 60 upward velocity component, the maximum height gain, you have to find that. Applied v square is equal to u square plus 2s for the initial projectile at the highest point 0 velocity, 400 sin 60 to minus 10 h max, 6,000 meters. So in this initial parabolic path, object will reach a 6,000 meter height. Here there's an explosion that separates this object into two equal fragments. At the highest point, no vertical velocity. So the after the initial parabolic path for the first half, this 2m mass, the complete mass got a velocity of 400 and 460 rightward direction. So 2m mass, 400, 460 is the initial momentum. After the explosion, one part falls down. That means instantaneously it has become to rest. That's why it fell down directly. M0, the other m with v. Calculated, I got the new velocity as 400 for the remaining fragment. Initially, as it's a complete body, it had only a velocity of 200 at the highest point. Now, after LMC, this remaining fragment has, other one fell down, remaining fragment got a larger velocity. So it will not follow the earlier parabolic path for the second half. It will move a different path, getting a higher range due to the high velocity gain after LMC. Meantime, anyway, it has to come 6,000 meters downward again to reach ground, and from there found the time. Within that time, with this horizontal velocity 400, it will gain a new range R dash from here to here. As they ask you as they ask you the complete horizontal range, first using the facts from the beginning, you have to find this R0 and you have to add that to this R dash. Getting the final answer, and you will get the answer in the tube. Okay, we are going to finish. Hari එහෙමනම් පරක්කු කරන්න යන්න පුළුවන්. හරි. 12යි 10යි වෙලාව නේද? හරි.